Hello there, and welcome to Science for Sleep, where curiosity drifts softly between stars and science takes its time to unfold. Tonight, we're turning our gaze outward, far beyond clouds and continents, to wonder about something that's both humbling and oddly comforting. Just how tiny is Earth, really, inside our own solar system? It's a strange thing to think about while lying in bed, surrounded by all the familiar sounds of your own world. To remember that the ground beneath you, the air you breathe, and the sky you see are all part of a sphere so small that from just a little distance it vanishes into a dot. A tiny bead suspended in the black. Yet that dot is home to everything we know, every story ever told, every thought that ever crossed a mind. There's something quietly miraculous in that, and maybe, just maybe, it's worth slowing down to feel it for a while. If you find this gentle wandering through space soothing, or simply a nice way to unwind after a long day, I'd be ever so grateful if you tapped like, maybe subscribed, or shared this sleepy corner with someone who might need a soft moment of wonder too. It helps this little community of quiet science drift a bit further into the night sky. So as you settle in and let your shoulders rest against the pull of gravity, imagine for just a moment that you're floating high above the Earth. Cities fade into patches of light, oceans melt into deep blue, the entire planet turns slowly beneath you, a living marble wrapped in thin swirls of cloud. It looks so complete, so solid, so large, and yet the higher you drift, the smaller it becomes, until the continents are only faint shades on a shining sphere, and even that sphere begins to shrink. From the orbit of the Moon, Earth is already just a shimmering coin, hanging beside its companion. From Mars, it's a spark, no larger than a distant star. By the time you reach the outer edge of the solar system, Earth disappears entirely into the background glow. The world that once filled your entire sense of existence becomes nothing more than a memory of light. Our planet isn't particularly large, at least not by cosmic standards. It measures about 12,700 kilometers across, a number that feels abstract until you start comparing it. Jupiter, the giant of our solar system, is more than 10 times wider. If Earth were a small marble, Jupiter would be a beach ball floating nearby, massive and striped with swirling storms. Even the Sun, that familiar circle in our sky, dwarfs us beyond comprehension. You could fit more than 1 million Earths inside it and still have room to spare. These aren't just numbers. They're a quiet reminder that we occupy a scale of existence that's far smaller than our senses suggest. But scale, in a strange way, is a human invention. We built it to help us understand, to give order to what the eye can't hold. The word small doesn't mean much to a star. Big means nothing to a galaxy. They are what they are, indifferent to our measures, and yet we can't help but reach for perspective. We stand beneath the night sky and try to grasp where we belong, how something so small can matter in something so vast. It's a kind of gentle puzzle that lulls the mind as much as it stirs it. Think of standing at the edge of the sea, watching waves stretch toward a horizon that never ends. The ocean feels enormous, but it's only a thin layer of water clinging to the planet's surface. If you shrank Earth down to the size of a billiard ball, its oceans and atmosphere together would form a glaze no thicker than varnish. All the storms, all the rain, every breath of wind that's ever carried a scent of spring or snow exist within that film. It's fragile, precious, and astonishingly thin. That realization can make the air in your room feel a little more meaningful, the quiet around you a little more connected to the universe beyond the window. From where you're sitting, the world feels vast. You could walk for years and never cross it all. Planes and ships and satellites travel endlessly around it, and yet it's only one grain of matter in a solar system so wide that even light, the fastest thing we know, takes hours to cross it. From the sun to Earth, light takes about 8 minutes. That means every sunrise is a message from the past, a glimpse of the sun as it was 8 minutes ago. To reach Neptune, the farthest major planet, light needs more than 4 hours. The outer edges of the solar system are so distant that our fastest spacecraft, travelling at tens of thousands of kilometres per hour, would take centuries to reach them. When you think about that, Earth's smallness becomes almost tender, a quiet island of warmth and colour adrift in a sea of night. If you could step outside the solar system entirely, you'd see the planets circling the sun like faint dust around a lamp. Mercury, Venus, Earth, and Mars would be tiny pinpricks clustered near the glow. Jupiter and Saturn would drift farther out, slow and stately. Uranus and Neptune, faint blue specks barely visible. The entire solar system itself, from the blazing core to the frozen rim, would fit easily within a tiny patch of the Milky Way, a galaxy so large it holds hundreds of billions of stars. Earth, by then, would be invisible, smaller than invisible, something only known by thought. And yet, we talk about it. We name it. We care about it. That care is what gives it weight in the vastness. Maybe that's why this question, how tiny is Earth, feels both humbling and comforting, because in knowing how small we are, we also realise how connected everything must be. The heat of the sun touches us across 93 million miles. The pull of Jupiter subtly shapes our orbit. The comets in the distant dark still whisper across the same gravitational web. The universe doesn't need to know us for us to belong in it. We're stitched into its pattern simply by being here. So, as we drift further into this quiet exploration, let's start at the scale we know best, the ground beneath our feet. From this tiny marble, every sunrise, every storm, every life plays out under the same thin sky. It's easy to forget that it's small when it contains so much, but step by step we'll widen our view, moving gently from our world to its neighbours, to the giants that keep company with us in this luminous system of spinning worlds. The night is long and there's plenty of room to wonder, so let's take our time, breathe softly, and begin to see our home for what it is. Not insignificant, not grand, but simply one small, beautiful thing among countless others, turning endlessly under the warmth of its star. When we start to think about size on a cosmic scale, something curious happens inside the mind. The idea of large and small begins to lose its grip, and the words we use to describe distance and mass start to feel fragile, stretched beyond their limits. On Earth, we live in a world of human proportions. A mountain is big, a pebble is small, an ocean is vast, and a cup of water is modest. These are scales that fit into our senses, that our brains can hold without strain. But when we begin to talk about the solar system, our sense of proportion bends, and the familiar rules we rely on stop working. Our comfort with scale comes from how we interact with our surroundings. A room feels spacious because we can cross it in a few steps. A city feels immense because it takes time to move through it. Even when we look at the sky, the moon seems close enough to touch, because our eyes can't grasp distance without reference. The truth is, human perception evolved for survival, not astronomy. We're built to judge whether we can reach a branch, not whether a planet is 50 million kilometers away. When you look up at the stars, what you're really seeing are projections, tiny bursts of light flattened against a black canvas by the limits of your senses. The moment we step beyond our world, we step into a scale that can't be felt. The mind has to invent ways to picture it. Scientists, poets, and teachers have all tried to shrink the universe down to something we can carry in our heads. One common comparison is to imagine the sun as the size of a door. If you did that, Earth would be smaller than a marble, placed a few meters away. Jupiter would be about the size of a grapefruit, orbiting far out across a parking lot. Neptune would be a pea rolling along the far curb. Even in this shrunken model, most of the space would be just that. Space. Empty, silent, cold. The planets themselves would take up almost nothing. That emptiness is one of the strangest truths about our solar system. is not crowded. It's not a cluster of planets packed close around the sun like beads on a string. It's almost entirely void, with distances so great that light, moving at nearly 300,000 kilometers per second, still needs minutes and hours to get from one place to another. Between Earth and Mars there is no border, no visible line dividing one planet's domain from another. There's just emptiness, the same dark canvas stretching on and on. That in itself changes how we think about scale. We tend to measure things by comparing them to each other, but in space, comparison loses its comfort. It's hard to feel large or small in a place where there's no edge, no container. And yet, even in that vast silence, we seek a sense of belonging. There's something deeply human in wanting to find our size in the grand picture, to ask where we fit, even when the answer keeps shifting. The comfort doesn't come from knowing exactly how big we are, but from realizing that everything, no matter its size, follows the same physical laws. The same gravity that holds the moon in orbit keeps a droplet of dew clinging to a blade of grass. The same sunlight that warms your hands has travelled across the same distance that nourishes entire planets. Size may separate, but the forces behind it unite. When you think about the sun's immense heat and gravity, it's easy to picture it as an overbearing presence dominating everything around it. But the relationship between the sun and its planets isn't one of domination, it's one of balance. Earth moves fast enough to keep from falling in, slow enough to stay bound. Every orbit in the solar system is a quiet agreement between motion and pull, a delicate equilibrium that has lasted for billions of years. From the outside it might look like chaos, spheres spinning through space at unimaginable speeds. But from within, it feels steady, rhythmic, and familiar. That rhythm gives us our days, our seasons, our heartbeat of light and dark. When you start to think about comfort in this way, it's less about warmth or safety, and more about predictability. The solar system, despite its scale, runs on patterns. Planets move in ellipses that repeat endlessly. The moon waxes and wanes. The sun rises, the sun sets. Even comets return on schedules measured in decades or centuries. For a being as small as a human, that predictability is a kind of reassurance. The universe might be large beyond comprehension, but it isn't random. Its vastness has order. Imagine you're floating again, looking down at the planets from above, drifting in that endless black. You see orbits tracing invisible rings around the sun, Mercury darting close and fast, Venus gleaming white in the heat, Earth blue and balanced, Mars rust red and calm. Farther still, Jupiter turning like a slow storm, Saturn's rings catching the faint light, Uranus and Neptune, serene and distant. From that view, none of them seem to compete for importance. Each simply exists in harmony with the others, their paths perfectly arranged by the laws of motion and gravity. That harmony is its own kind of comfort. We tend to think of smallness as a kind of weakness, but in cosmic terms, it's what allows us to exist at all. If Earth were much larger, gravity would crush us. If it were smaller, the atmosphere would drift away. Our size relative to everything else is a balancing act between extremes. Even our sun, though massive compared to the planets, is just a middleweight among stars. There are others out there thousands of times larger, burning hotter, brighter and faster. Yet if our sun were one of those giants, its lifespan would be short, and life here would never have had time to begin. Smallness, it turns out, can be a kind of quiet perfection. The cosmic scale is both overwhelming and deeply grounding. When we think about the billions of kilometers between planets, the years it takes light to cross the space between stars, it's easy to feel insignificant. But insignificance is just one interpretation. The other is awe. To realize that our tiny planet is part of something so vast and interconnected can make you feel not lost but found. The same way standing under a clear night sky can make the world feel both huge and intimate at once. It's interesting to consider how our sense of size shifts depending on context. A grain of sand on a beach is easy to overlook, yet that grain, under a microscope, is intricate and unique. A single cell, invisible to the naked eye, holds within it machinery more complex than any city. Scale doesn't define importance, it just defines perspective. In the same way, Earth's size doesn't make it less meaningful in the solar system. It makes it the perfect scale for the life that evolved upon it. The vastness around us doesn't diminish us. It frames us. Humans have always tried to measure that frame. The earliest astronomers tracked the motion of planets across the sky, long before anyone knew what they were. Those slow wanderers became reference points, ways to make sense of time and distance. Even now, when we send spacecraft to explore them, we're still measuring, still comparing. We stretch our imaginations across billions of kilometers, not because we expect to conquer them, but because it brings a kind of peace to understand them. Knowing where we are is one of the oldest forms of comfort. The scale of the solar system isn't just a matter of numbers, it's a story about how we fit into a pattern. The sun gives energy, planets receive it, moons reflect it. Comets carry ice and dust from the outer reaches back toward the warmth. Asteroids drift between orbits, silent markers of creation. Every piece, from the tiniest grain of interplanetary dust to the heaviest planet, plays a role in the balance. Earth's role, while small, is no less important. It's the place where matter became aware of itself, where the universe began to ask questions about its own size. So, as we continue moving outward through this quiet solar neighborhood, keep that balance in mind. The distances will grow, the numbers will stretch, and the comparisons will start to lose their meaning. But the feeling, that mix of humility and belongings, will stay. The more we see how small we are, the more we understand the beauty of being exactly this size. Because somewhere in the rhythm of orbits and the silence between stars, our little planet finds its place not by size but by harmony. When you start thinking about Earth not as the world under your feet but as an object in space, the idea feels almost impossible to hold. Here, everything seems so solid. Mountains rise, oceans stretch, buildings reach upward, and the ground feels endless when you walk across it. Yet all of it together, everything that ever lived or moved or spoke, is clinging to a sphere only a little more than 12,000 kilometers wide. From space, that sphere looks polished, smooth, and fragile, glowing faintly in the light of a star. There are no borders, no names, no sound, just a marble turning slowly in a silent current of sunlight. The first humans to see Earth from outside it tried to describe the view, but most found words too small for what they felt. Astronauts spoke of awe, loneliness, and connection all at once. The photographs they brought back showed our planet suspended in blackness, half lit, half in shadow, its blues and whites wrapped together like smoke over glass. They called it the blue marble, a simple phrase that somehow carried everything. It's strange how a single image can change the way a species thinks about itself. Before that photograph, most people thought of the world as a map. After it, the world became one whole thing, round and finite, bounded by the thin veil of its atmosphere. If you could hold Earth in your hands, it wouldn't feel smooth. You'd feel the mountain ranges, the trenches, the irregular scars of craters and ridges. But from even a few thousand kilometers away, all those details disappear. The Himalayas, the Andes, the Grand Canyon, all dissolve into a single seamless curve. The tallest mountain, Everest, rises less than 9 kilometers above sea level. On a globe the size of a basketball, that's less than the thickness of a fingerprint. The atmosphere that keeps you alive is even thinner. If the planet were that basketball, the breathable air would be a layer of mist thinner than a coat of paint. Everything we know fits inside that film. When sunlight hits it, that film glows. The oceans scatter the light into shades of blue, and clouds reflect it into white. From space, the continents are dark greens and browns. but what stands out most is the colour of water. More than 70% of the surface is covered in it, and the rest is wrapped in the same cycle of evaporation and rain. From orbit, there's no sign of roads, no walls or cities. Civilization vanishes into the texture of the planet. The sight of it has a strange stillness. You realise that everything happening below, all the motion, all the noise, is part of a quiet pattern that, from a distance, looks perfectly calm. The word marble fits because it carries a sense of something both solid and decorative. A marble is meant to be held, to be admired, to roll and catch the light. But Earth is not a toy in anyone's hand. It's balanced between forces that could tear it apart or freeze it solid. Gravity holds its shape. The spin gives it rhythm, and the energy from the sun keeps it warm enough for liquid water to exist. That combination, size, distance, atmosphere, and motion, is so precise that it feels less like chance and more like harmony. The marble isn't just small, it's tuned. If you could drift just above the atmosphere and watch Earth rotate, it would complete a turn every 24 hours, about one rotation every 1,000 miles per hour at the equator. Yet from space it looks peaceful. The clouds move in slow spirals, the oceans glimmer in faint light, and the terminator line, the boundary between day and night, slides across the surface like a soft shadow. You could spend hours watching it and still feel you were seeing something alive. The weather, the currents, the slow pulsing of light and dark, all of it looks like breathing. What's surprising is how small that breath is in cosmic terms. The entire planet orbits the Sun at about 30 kilometers per second. It seems fast until you remember that the solar system itself is moving too, carrying Earth, the Moon, and everything else around the galaxy at more than 200 kilometers per second. All that speed, all that motion, and yet it feels still here on the surface. The stability you feel under your feet is an illusion of scale. The marble is spinning and flying through space, but you are moving with it perfectly, caught in its grip. Sometimes people imagine shrinking the solar system down to a scale model to make sense of these proportions. If the Sun were the size of a large doorway, Earth would be smaller than a pea placed a few meters away. The Moon would be a grain of sand circling that pea. The distance between Earth and the Sun in this model would be enough to walk across a room, but to reach Neptune, the edge of the planetary family, you'd have to cross several city blocks. The solar system is almost empty space, and our marble floats in that emptiness, a lone sphere warmed by one nearby star. When you look at Earth from a high orbit, the colour shifts slightly with each rotation. Clouds form and dissolve, continents drift into view and fade again. The blue deepens near the edges where the light scatters through more air. It's the same blue that fills your sky during the day. That's another trick of perspective. From the surface, the sky seems endless. But from space, it's just a thin band around the planet, fading into black within a few minutes of travel upward. The line between day and night, between light and dark, between warm and cold, all fits inside that narrow gradient. It's easy to forget that this view didn't exist for most of human history. For thousands of years, people imagined Earth in every shape but a sphere. It took careful observation, mathematics, and patience to understand that the world curved back on itself. Even then, it remained an idea until we finally saw it from above. The first photographs from orbit changed more than science. They changed awareness. To see Earth as a whole was to see it as fragile. It didn't look infinite or invulnerable. It looked delicate, almost transparent. And that shift in perception began to influence how people thought about the environment, about life, about what it means to belong to a single planet instead of a single place. Every time an astronaut looks out at the Earth, they describe something called the overview effect. It's a change in perception that comes from seeing the planet as one complete thing. Boundaries vanish, and so do divisions. You can see the curve of the horizon, the thin shimmer of the atmosphere, the gentle swirl of clouds that ignore every human line. The effect isn't mystical, it's psychological. When you see the whole, you understand that everything is connected, not metaphorically, but physically. The air in one hemisphere becomes wind in another. The ocean's current carries warmth and salt from one continent to the next. The marble doesn't divide, it unites through motion. Even with all our technology, we've barely touched the surface of that marble. Most of the ocean depths remain unseen. Much of the planet's core is inferred only by seismic vibrations and theory. The crust we live on is just the outer shell of a much deeper structure. Mantle, outer core, inner core, each layer behaving differently under pressure. If you were to travel straight downward, you'd pass from solid rock to molten metal to a dense sphere of iron at the centre. That inner core, no larger than the moon, rotates slightly faster than the rest of the planet, generating the magnetic field that shields us from solar radiation. The marble glows not only from sunlight, but from its own hidden energy, stored since its formation billions of years ago. Earth formed from dust and gas orbiting the young sun, pieces colliding and merging under gravity's pull. The early planet was molten, bombarded by asteroids, its surface constantly reshaping. Over time it cooled, crust solidified, oceans formed, and life began in microscopic forms. Every grain of sand, every drop of water, every cell in your body traces back to that process of accumulation and change. The marble we live on is ancient, yet it's still in motion, still evolving. Continents drift, climates shift, species appear and vanish, all as part of a long pattern written into the rock itself. From the outside, none of that is visible. You can't see evolution, plate tectonics, or civilization from space. What you see instead is colour and light. City lights glow faintly on the night side, forming webs across continents. Storms spiral over oceans. Lightning flashes like tiny pulses. It's as if the marble has veins of energy running through it, flickering between natural and artificial light. That faint glow is another kind of signature, evidence that life and thought exist on this small world. The solar system is mostly cold and silent, but this marble hums with motion. If you imagine the planets as family members around a table, Earth would be one of the smaller ones, but the most animated. Mercury and Venus have no moons. Mars is smaller and colder. Jupiter and Saturn are enormous, but made mostly of gas, too turbulent and hostile for surfaces or seas. Earth sits between them, neither too near nor too far, solid but not static, a place where sunlight and gravity and chemistry reached a balance that allowed complexity to grow. The marble's size makes that balance possible. A little bigger, and its gravity would hold too much atmosphere. A little smaller, and it couldn't hold any at all. It's just right, not by design but by probability, a happy outcome in a universe of extremes. The idea that such a small planet can contain so much variation is another quiet marvel. From the edge of space you can see deserts and forests in the same glance. You can see snow over one pole and storms over the other. The marble is small, but its surface carries nearly every condition imaginable: heat, cold, wet, dry, high, low. Life has adapted to all of it. Every ecosystem, from coral reefs to mountain peaks, fits into the same limited shell. When you realise how thin that shell is, every tree, every breath of air feels significant. Some people find this realisation comforting. Others find it unsettling. To know that our world is small is to understand how easily it could change, how vulnerable it is to forces beyond our control. But it's also a reminder of resilience. For billions of years, through impacts, ice ages and extinctions, the marble has remained. It has kept its orbit, its tilt, its spin. It has carried life through cycles of disaster and renewal. In cosmic time, that persistence is remarkable. When you picture the solar system from above, Earth is a dot among dots, but the fact that we can picture it at all says something about awareness itself. The marble beneath our feet isn't just a planet, it's a mirror reflecting the universe back at itself. Everything that exists here, the oceans, the clouds, the people thinking about them, are pieces of the cosmos arranged just right to see and understand themselves. From that perspective, smallness doesn't feel limiting. It feels like participation in something much larger. As the view widens and the light from the sun stretches farther, that small blue world begins to blend with its surroundings. The line between home and the rest of space fades, and Earth becomes one of many. Yet the feeling of looking back at it never fades. No matter how far away you drift, that marble still draws the eye, still reminds you that small things can hold entire histories inside them. When you start looking beyond Earth, the neighbourhood opens up in a way that feels both familiar and foreign. The planets of our solar system are companions in motion, each following its own path around the sun, bound by the same gravity, warmed by the same light, yet completely different in personality and scale. They share a family resemblance only in orbit. Everything else about them, from colour to climate to composition, tells a story of extremes, and as soon as you place Earth among them, its modest size becomes clear. The planet nearest to the Sun is Mercury, the smallest of the 8. If you could stand on its surface, the Sun would look twice as large as it does from Earth, blazing across a sky without clouds or air. Mercury is only about a third the width of our planet, roughly 4,800 kilometers across, smaller than some of Earth's continents. With almost no atmosphere to protect it, temperatures swing from blistering heat to freezing cold, hundreds of degrees apart between day and night. The sky there is black, even in daylight, because there's no air to scatter sunlight. It's a place where shadows are sharp and silence absolute. Despite its size, Mercury moves quickly, circling the Sun in just 88 Earth days. Its name suits it. The Roman messenger god was swift, and this planet lives up to that pace. Seen from above, it hugs the Sun tightly, darting through space like a stone on a string. Compared to it, Earth's orbit feels leisurely, yet even here, at the innermost edge of the system, the scale is deceptive. The gap between Mercury and Venus is over 50 million kilometers. You could fit all the other planets between them with room to spare. For something we call a neighbourhood, the spacing is immense. Next comes Venus, nearly the same size as Earth, a twin in dimensions but not in temperament. Its diameter is just a few hundred kilometers smaller than ours, but the resemblance ends there. Venus wears a blanket of thick clouds made of sulfuric acid, trapping heat so effectively that its surface temperature is hot enough to melt lead. The pressure on the ground is so intense that landers survive only a few hours before being crushed. If you could somehow look out across its horizon, you'd see a dim orange glow filtered through dense haze. The sun would be invisible, hidden behind endless cloud. Wind moves slowly there, and the air is toxic. And yet, from a distance, Venus shines brighter than any other planet in the night sky, outshining even the brightest stars. Beauty hiding hostility. When you compare Earth to Venus, the smallness of our own world feels less significant than its good fortune. Two planets so similar in size orbiting the same star can lead such different lives. The delicate balance that makes Earth habitable, distance, atmosphere, temperature, could easily have tipped the other way. We might have been the inferno and Venus the oasis. Instead, we orbit just far enough for water to remain liquid, for skies to stay blue, and for the marble beneath our feet to nurture life. Beyond Earth lies Mars, smaller and colder, its surface tinted by iron oxide that gives it a dusty red glow. It's about half the size of Earth, with gravity just a little over a third of what we're used to. A human weighing 70 kilograms here would weigh barely 25 there. The air is thin, mostly carbon dioxide, and the wind can rise into planet-wide dust storms that last for months. But for all its harshness, Mars feels strangely familiar. It has valleys and mountains, polar ice caps and seasons. Olympus Mons, its tallest volcano, rises nearly 3 times higher than Everest, and Valley Marineris, a canyon system stretching over 4,000 kilometers, would stretch across the width of the United States. The planet may be small, but its features are grand. For decades, Mars has captured imagination more than any other world. It's near enough for spacecraft to reach, solid enough to land on, and mysterious enough to keep us wondering. When you look at photographs from its surface, the rocks and hills look almost Earth-like, just painted in red. In those images, Earth itself appears as a pale blue point in the dusty Martian sky. That view reverses perspective. The observer becomes the observed. From Mars, the blue marble is just another star. Between Mars and Jupiter lies the asteroid belt, a wide region of scattered rock and metal. It isn't crowded, despite what old movies once showed. The average distance between asteroids is millions of kilometers. Some are as small as pebbles, others as large as mountains. Ceres, the largest of them, is big enough to be called a dwarf planet, about 900 kilometers wide. The belt is like a cosmic construction site left unfinished, fragments that never gathered into a full planet because Jupiter's gravity kept tugging them apart. Even here, in what seems like empty space, the distances dwarf our imagination. Then comes Jupiter, the first of the giants, and the point where the scale of our world becomes almost unthinkable. Jupiter is 11 times wider than Earth and more than 300 times as massive. If Earth were a marble, Jupiter would be a beach ball, swirling with storms the size of continents. Its great red spot is a hurricane so large that 3 Earths could fit inside it. The planet's atmosphere is made mostly of hydrogen and helium, and there's no solid surface beneath those clouds, only layers of gas growing denser until they merge into a metallic sea. Orbiting Jupiter are more than 90 moons, each with its own peculiar landscape. Ganymede, the largest, is even bigger than Mercury. Europa, smooth and bright, hides an ocean beneath its icy crust, an entire sea kept liquid by the planet's gravitational pull. When you think of Earth's oceans, vast as they are, they may not even be the largest bodies of water in the solar system. That title might belong to Europa, a moon orbiting a giant so massive that it bends space around it. The contrast between our marble and this immense sphere is staggering, but it's also fascinating that both worlds, large and small, share the possibility of ocean and ice. Farther out is Saturn, a world almost as large as Jupiter, but more graceful in appearance. Its rings, made of countless particles of ice and dust, stretch hundreds of thousands of kilometers wide, yet remain only a few dozen meters thick. Through a telescope, those rings look delicate, almost decorative, but they're the remains of shattered moons or failed formations. Saturn itself could fit about 9 Earths across its diameter. Like Jupiter, it's made mostly of gas, but its density is so low that it would float in water, if you could find a cosmic ocean big enough. Its many moons, especially Titan, reveal another layer of complexity: methane rivers, lakes, and a thick orange atmosphere. Titan is nearly the size of our moon, yet it behaves more like a planet. Past Saturn, the solar system feels colder, quieter, more remote. Uranus tilts on its side, rolling through its orbit rather than spinning upright. Its pale blue colour comes from methane in its atmosphere, which absorbs red light and reflects blue. At 4 times Earth's size, it's still overshadowed by the giants before it, but its tilt creates seasons unlike any other world. Each pole spends decades in sunlight, followed by decades in darkness. Neptune, the last of the major planets, is similar in size but deeper in colour. Its winds are the fastest in the solar system, reaching speeds of more than 2,000 kilometers per hour. Both planets, though vast, are still just faint dots even in powerful telescopes. And then, beyond them, the sun's warmth fades into a region of frozen debris and distant comets, the outermost boundary where the solar wind meets the interstellar medium. From that edge, the planets seem like beads of light strung across a void. Earth's orbit, wide and endless to us, looks tiny from there, barely noticeable beside the giants. The family of planets stretches across billions of kilometers, yet all are held together by the same invisible thread of gravity. Looking at them as a whole, the pattern becomes clearer. The small rocky worlds lie near the Sun. The large gaseous ones occupy the outer reaches. It's as if the early solar system sorted itself by material and temperature. Metals and silicates near the heat, hydrogen and helium farther out where it could condense. Earth sits in the middle, balanced between these two realms. That position, neither too hot nor too cold, has made all the difference. What's striking about this family of worlds is how each reveals something about the rest. Mercury shows us what happens when there's no air. Venus warns what happens when there's too much. Mars shows the cost of losing it. Jupiter and Saturn reveal how massive planets shape their systems, and the ice giants remind us that even the faint edges of sunlight can still sustain structure and beauty. Against that backdrop, Earth's smallness feels less like limitation and more like precision. Everything about it fits into the solar pattern in a way that allows complexity to emerge. The neighbourhood may be vast, but it's still a neighbourhood, a collection of worlds circling a shared light. Each one moves to the same rhythm, completing its orbit in silent cooperation with the rest. No collisions, no chaos, just motion governed by gravity's steady pull. And somewhere in that grand choreography, our little planet keeps turning, carrying seas, forests, and sleeping minds beneath its thin air. If Earth is a marble turning quietly in the light, then Jupiter is the giant standing beside it, a vast and restless presence that defines the rhythm of the solar system. Calling it large doesn't quite capture it. Jupiter is more than just big. It is enormous beyond ordinary language. Its width is 11 times that of Earth, its volume so immense that more than 1,000 Earths could fit inside it with room left over. Even so, it's made mostly of gas, hydrogen and helium, the same ingredients as the Sun, but without the mass needed to ignite into a star. It sits on the edge of two identities, too small to shine, too big to ignore. From Earth, it looks like a bright, steady light in the night sky, unblinking and almost serene. Through a telescope that calm dissolves into motion, Jupiter's atmosphere is a whirl of storms, stripes, and shifting bands of colour. The Great Red Spot, a vortex larger than our entire planet, has been raging for at least 400 years, possibly longer. It's not a crater or a stain, but a cyclone so vast that it could swallow Earth 3 times over and still have space to spare. Around it, smaller storms come and go, changing shape and colour as they twist through the planet's upper layers. What you're seeing in those stripes isn't solid ground, but clouds made of ammonia and water, moving at hundreds of kilometers per hour across a sea of gas. Beneath those clouds, there is no surface to stand on. If you descended into Jupiter, the atmosphere would thicken gradually until it crushed you with pressure and heat. The gases would compress into liquid hydrogen, then metallic hydrogen, a state that doesn't exist naturally anywhere on Earth. The deeper you go, the stranger it becomes, dense, hot, and alien. Somewhere below, perhaps, there's a rocky core, but no probe has ever seen it. Jupiter hides its secrets behind a cloak of storms. Despite being more than 600 million kilometers away, the planet's presence shapes Earth's environment. Its gravity is immense, strong enough to bend the paths of asteroids and comets. In many ways, Jupiter acts as a guardian, deflecting or capturing objects that might otherwise strike the inner planets. Some scientists think life on Earth might owe its survival, at least in part, to this gravitational shield. The same pull that keeps dozens of moons in orbit around Jupiter has also swept countless rocks into safe orbits, or sent them drifting harmlessly into deep space. The giant's reach extends far beyond what the eye can see. When you think about size in the solar system, Jupiter resets the scale. Earth, so full of life and motion, becomes a small companion in comparison. Jupiter's magnetic field is 14 times stronger than Earth's and stretches millions of kilometres into space, forming a vast invisible bubble of charged particles. If you could see that field with your eyes, it would appear larger in the sky than the full moon. Its moons orbit within that bubble, caught in a magnetic storm that never ends. Radiation there is fierce, enough to destroy electronics or harm living tissue within minutes. Yet within that danger, there's beauty. The auroras near Jupiter's poles glow brighter and more powerful than any seen on Earth, wrapping the planet in curtains of blue and violet light. Jupiter's system of moons is a miniature solar system of its own. There are more than 90 confirmed, each unique. The 4 largest, Io, Europa, Ganymede and Callisto, were first seen by Galileo in 1610. He didn't know it then, but that discovery would change science forever. It was proof that not everything revolved around Earth. The universe, it turned out, had centres of motion everywhere. Io is the most volcanically active body in the solar system, its surface covered in lakes of molten rock. It's constantly reshaped by Jupiter's gravity, stretched and squeezed as it orbits. The friction inside heats it from within, keeping it in perpetual eruption. Europa, smaller and smoother, is covered in a layer of ice. Beneath that ice lies an ocean deeper than any on Earth, possibly twice the volume of all our planets combined. Scientists suspect that ocean might harbour the conditions for life, dark, pressurised, and warmed by the same gravitational energy that keeps Io molten. Ganymede, larger than Mercury, has its own magnetic field and signs of subsurface water. Callisto, cratered and ancient, is like a museum of impacts, its surface unchanged for billions of years. To stand on any of those moons, if one could, would be to look up at a sky dominated not by a sun but by a planet so vast it fills the horizon. Jupiter would appear dozens of times larger than the moon does from Earth, glowing in soft gold and cream. You'd see storms rolling across it in slow motion, lightning flashes hundreds of kilometres long, clouds shifting like tides. The light from the distant sun would reflect off the planet's upper atmosphere and bathe everything in pale radiance. Night and day they would blur together under the constant presence of that giant face in the sky. It's easy to imagine Jupiter as a symbol of dominance, but it's more accurate to think of it as balance. Its gravity helps stabilise the solar system's architecture. Without it, the orbits of smaller bodies might wobble out of alignment. Its mass creates order through attraction, gathering dust, ice and rock into orbits instead of letting them drift aimlessly. Even its storms, though violent, have structure, repeating patterns that obey the same physics as the breezes on Earth. The scale changes, but the rules remain the same. When we send spacecraft to study Jupiter, Pioneer, Voyager, Galileo, Juno, they don't orbit for long. The radiation would destroy them if they stayed. Instead, they fly past or skim close, gathering data as they go. The images they send back reveal colours too subtle for the naked eye. Ochre, ivory, copper, and grey, swirled together like oil on water. The patterns look alive, but they follow the flow of physics: heat rising, cold sinking, storms merging, winds crossing at high speed. The planet may be inhospitable, but it's never lifeless in motion. Jupiter's sheer size makes it a point of reference for everything else. Astronomers often measure other planets by how they compare to it. Gas giants around other stars, exoplanets, are frequently described as Jupiter-like or smaller, heavier or hotter. Its existence becomes a baseline, a familiar constant in a universe of unknowns. Even in that context, Earth remains an exception. Small, rocky, blue, a world of water instead of gas with a surface instead of clouds. The difference between the two worlds is more than size, it's essence. Jupiter is magnitude, Earth is intricacy. One overwhelms, the other refines. If you think of the solar system as a living system, Jupiter is its heart. It's not the source of energy, That's the sun, but the stabilizing force that keeps everything beating in rhythm. The smaller planets move safely within its gravitational influence, and the outer planets follow its lead. It may be a world we can never stand on, but its role is as crucial as any solid ground. Every storm on Jupiter, every orbit of its moons, adds to the harmony of the solar system's motion. For all its size, Jupiter is still just one of many giants. Beyond it lies Saturn, less massive but no less striking. If Jupiter is power, Saturn is elegance, a planet wrapped in the most delicate structure in the solar system, a series of rings so broad and thin they seem impossible. To move from Jupiter to Saturn is to see the difference between mass and grace, between raw magnitude and symmetry. The farther we travel, the more Earth seems to shrink, its orbit receding into the distance like a single bright bead on a string of worlds that stretches far beyond our reach. And still, even as the scale grows, the same question lingers in quiet ways. What does it mean to be small in a system of giants? Jupiter, Saturn, and the others may dwarf our planet in size, but not in meaning. The marble remains unique, carrying life and awareness through a system of immense silent bodies. Each world adds a layer to the story, and together they define the range of what a solar system can be, from burning heat near the sun to frozen calm at its edge. Jupiter, the giant next door, is only one part of that story, but without it, the rhythm of everything else would change. Far beyond Earth's orbit, past the familiar shimmer of the inner planets and the vast presence of Jupiter's storms, lies a place where sunlight begins to weaken into something softer. It doesn't vanish, but it fades, spreading thinner across the distance. Here, Saturn drifts, a pale yellow sphere wrapped in the most delicate structure ever seen in the solar system. For centuries, even through early telescopes, people could sense there was something strange about it. Galileo saw the planet's sides bulge and thought they might be handles. Later observers realized what they were: rings. Now, with clear images from spacecraft, we know that those rings are not solid at all, but billions of tiny pieces, each orbiting Saturn separately, each reflecting sunlight in its own slow rhythm. When you look at Saturn in pictures, the rings seem fragile, almost like light itself. But they're made of real material, water ice mixed with dust and rock. Some pieces are no bigger than grains of sand, others the size of boulders. If you could somehow stand inside them, they'd look like a glittering field stretching in every direction, mostly empty space between chunks that move so fast they never collide for long. Each fragment follows its own orbit, but together they form bands, bright and dark, wide and narrow, that stretch hundreds of thousands of kilometers from the planet's equator. Yet for all that distance, the rings are astonishingly thin. In most places, they're no thicker than a few stories of a building. From far away, they seem to vanish at the edge, like a line drawn in air. The light that hits those rings doesn't stay constant. As Saturn moves around the Sun, the angle of sunlight shifts, changing their brightness. Sometimes they shine like fresh snow, sometimes they dim to a faint grey. Every 12 to 15 years, they even seem to disappear when seen from Earth, vanishing edge-on before reappearing from the other side. It's an illusion of perspective, a cosmic sleight of hand that reminds us how much the view depends on where we're standing. Up close, Saturn is even larger than it appears. Its diameter is about 9.5 times that of Earth. It's less dense than water, a giant ball of hydrogen and helium, with a small rocky core hidden under layers of metallic hydrogen. Like Jupiter, it has no solid surface, only clouds moving in bands and storms swirling in slow motion. Winds there can reach more than 1,000 kilometers per hour. Around the poles, strange geometric storms form, most famously the hexagon at the North Pole, a six-sided pattern in the clouds that stretches wider than our planet. It isn't a shape carved in stone, but a stable atmospheric wave. a natural product of rotating fluids on a massive scale. The symmetry feels precise, almost artificial, yet it's born from physics alone. Saturn's rings aren't eternal. Over millions of years they may fade as collisions grind their particles smaller and gravity pulls the dust into the planet's atmosphere. Some scientists think they might even be temporary, a feature that came and will eventually go, forming again someday from new debris. In cosmic time, even something so vast can be fleeting. The thought of that transience gives them a kind of quiet beauty, a reminder that even in the scale of planets, nothing lasts forever. Orbiting Saturn are more than 100 moons, ranging from tiny irregular stones to Titan, a world nearly the size of Mercury. Titan is thickly wrapped in atmosphere, a rare thing among moons. Its sky is orange, its surface hidden under haze. When spacecraft finally glimpsed it, they found lakes and rivers, but not of water, of liquid methane and ethane, hydrocarbons flowing slowly in the cold. Temperatures there are nearly 200 degrees below freezing. The methane behaves like water does on Earth, evaporating, condensing, raining down again in cycles. Titan has weather, erosion, and maybe even a kind of chemistry that could, under the right conditions, hint at life. Another moon, Enceladus, is smaller but even more intriguing. Beneath its icy crust lies a global ocean, kept liquid by tidal forces from Saturn's gravity. From cracks near its south pole, jets of water and vapour shoot into space, forming plumes that arc high above the surface. Those jets feed some of Saturn's rings, recycling matter between moon and planet. When the Cassini spacecraft flew through those plumes, it detected organic molecules, carbon-based ingredients for life. It doesn't mean anything is alive there, but it means the basic materials are present, sealed beneath ice, warmed by motion, waiting in the dark. The moons around Saturn vary so much that they seem like a collection of experiments in miniature. Mimas is cratered and battered, with one enormous impact crater that makes it look like an eye staring back at the universe. Tethys and Dione reflect light like fresh snow. Rhea, another moon, may have rings of its own, thin and faint, almost ghostly. Iapetus has one hemisphere bright as frost and the other dark as coal, a world divided cleanly in two. Each moon keeps a unique record of collisions, orbits, and composition. Together, they make Saturn's system one of the most diverse environments in the solar system. From a distance, Saturn and its rings look serene, but in motion they're full of complexity. The gaps between the rings aren't empty by chance. They're carved by the gravity of the moons, which create resonances, places where their orbital periods match fractions of Saturn's rotation. The gravitational pull tugs on the ring particles at precise intervals, clearing paths and shaping edges. It's a dance of timing and mass, invisible yet exact. Without those interactions, the rings would be a blur. With them, they form structure. The same physics that shapes waves in the ocean shapes the arcs of ice around Saturn. When sunlight passes through the rings, it casts faint shadows onto the planet's clouds below. Those shadows shift as the planet moves, dark ribbons that slide slowly across the surface. From space they look like brushstrokes across the globe. The sight gives the impression that the planet itself is aware of its adornments, wearing them not as decoration but as part of its identity. The rings and shadows belong together, light and absence of light intertwined in motion. If you could hover above the rings and look down, the perspective would change everything. The planet would fill half the sky, its atmosphere glowing softly, its pole-shaped storms turning endlessly. Below you, the rings would stretch outward in every direction, countless fragments catching the sunlight and throwing it back in flickers. Each piece would move too quickly to see, but together they'd appear still, the illusion of calm born from speed. The emptiness between them would dominate your view, reminding you again that the solar system is mostly void. In that quiet emptiness, Earth feels very far away. Its orbit, full of sunlight and warmth, lies hundreds of millions of kilometers closer to the Sun. The light that reaches Saturn has travelled more than an hour to get there, weakened to a faint glow compared to what we see at home. Yet even in that distance, there's a connection. The same sunlight that warms your skin is the same energy that glitters off Saturn's rings, reflected back into the dark. The photons that left the Sun minutes ago for Earth left an hour ago for Saturn. The scale of time stretches, but the relationship stays constant. Saturn's beauty lies not only in its appearance but in its role. It too shapes the system around it. Its gravity affects Jupiter and the outer planets, maintaining balance. Its moons, pulled by that same gravity, heat and cool in cycles that create oceans, atmospheres, and icy plumes. It's a world of relationships, bound by invisible forces that extend across billions of kilometers. Nothing in the solar system exists alone. Every orbit, every shadow belongs to the pattern. For scientists and dreamers alike, Saturn marks a threshold. Beyond it, the solar system grows colder, quieter, and stranger. The next planets, Uranus and Neptune, are smaller than Jupiter and Saturn, but still massive enough to hold their own systems of moons and faint rings. Past them lies the Kuiper Belt, where Pluto and countless icy bodies drift near the edge of the Sun's reach. Looking from Saturn's orbit toward the inner solar system, the Sun appears bright but small, a disk no larger than a coin held at arm's length. Earth, from here, is invisible to the naked eye, hidden somewhere in that glow. Yet even from this distance, our planet's smallness carries a kind of meaning. All of the light, heat, and life that Earth knows comes from that distant point. Everything about the world, the warmth of summer, the rhythm of tides, the comfort of daylight, depends on energy that has crossed that empty space. The rings, moons, and shadows of Saturn reflect the same light we live by, but they use it differently, quietly, without life, without awareness. Still, they are part of the same story, the marble and the giant, the bright rings and the faint moons, all moving together through the slow drift of time. Between the orbit of Venus, where heat burns through clouds thick as oceans, and the orbit of Mars, where frost collects even in daylight, lies a narrow zone that seems almost like an accident of luck. It is neither too close to the Sun nor too far. Astronomers call it the habitable zone, a simple phrase for something astonishing. The region where liquid water can exist on the surface of a planet. Earth moves through the middle of that zone, keeping an orbit so stable that for billions of years its seas have neither boiled away nor frozen solid. This is where warmth and cold reach a kind of truce. It's a balance not of stillness but of motion, a constant negotiation between the energy falling from the Sun and the heat radiating back into space. When you think about that balance, it becomes clear how delicate it is. A small shift in distance, a slight change in atmosphere, a modest tilt in rotation, and the result would be completely different. Earth's average temperature depends on sunlight filtered through a sky that scatters blue and traps infrared. The thin layer of gases above us, mostly nitrogen, oxygen, water vapour and a trace of carbon dioxide, acts like an insulator, letting light in and slowing its escape. It's not much, barely a fraction of a percent of the planet's mass, but without it, the oceans would freeze and the surface would become a desert of ice. With a little too much, it would swing the other way, trapping so much heat that the seas would boil and the air would turn toxic. The space between those outcomes is narrow, but within it lies everything we know as life. The warmth we feel on Earth isn't a property of the planet itself. It's borrowed sunlight. Every photon that touches your skin began as a reaction in the core of the Sun, a process that turned hydrogen into helium, releasing light that took hundreds of thousands of years to move from the solar interior to the surface, and then just over 8 minutes to cross the emptiness between us. By the time it arrives here, it is scattered through clouds and air, absorbed by oceans and forests, reflected by ice and stone. That energy runs everything. Plants turned it into sugar. Winds carry its uneven heat across continents. The balance of day and night, of summer and winter, of growth and rest, all stem from this constant exchange of light. Compared to the outer planets, Earth receives an abundance of warmth. Saturn's sunlight is 100 times weaker. Neptune, the farthest major planet, sees only a faint glow, a brightness so dim that noon there would look like deep twilight to human eyes. And yet even here, near the centre of the system, warmth is not constant. It shifts with the planet's tilt, with the angle of its orbit, with the clouds that gather and part. Every fraction of sunlight matters. The warmth that reaches your window on a summer morning has travelled 93 million miles, and still arrives in just the right amount to raise air temperatures, melt ice, and sustain the cycle of life. Cold, though, is just as vital. Without it, the atmosphere would hold no rain. The difference between warm and cold drives the weather, the motion of air and water that redistributes heat. Evaporation, condensation, and precipitation depend on that tension. The cold traps the heat where it's needed and stores it in ice, glaciers, and currents. The poles, wrapped in frost and shadow, act as mirrors reflecting sunlight back into space, preventing runaway warmth. The line between them, the temperate zones where most life thrives, is a moving boundary, constantly adjusting but never vanishing. If you could step back and look at Earth from space, you'd see this balance painted across its surface. The equator glows in gold and blue, surrounded by bands of clouds that move like slow rivers. Closer to the poles, the colours fade to white and grey. Storm systems spin, carrying heat from the tropics toward the cold. The planet breathes through this movement. The winds, the rains, the tides, all of them are the language of energy finding equilibrium. It isn't peace in the sense of stillness, it's balance in motion, a continuous adjustment that has lasted for billions of years. The moon plays its part in that rhythm. Its gravity stirs the oceans, pulling tides that mix warm and cold water. The daily rise and fall of the sea isn't just scenery, it's part of the planet's thermostat. Without tides, the oceans would stratify into layers and the surface might heat unevenly. The rotation of the Earth spreads the warmth as well. Every 24 hours the sun traces its path across the sky, heating one side and cooling the other. That cycle, repeated endlessly, keeps temperature differences from becoming extremes. The planet spins like a pot turning over a fire, ensuring the heat distributes evenly enough for life to endure. But that warmth and cold are always changing. Over geological time, the planet has slipped through ice ages and warm periods, swings that follow slow changes in orbit and tilt. Sometimes the difference is subtle, only a few degrees, yet enough to transform landscapes, sea levels, and ecosystems. The Earth's climate is a record of its long conversation with the sun, one that speaks in glaciers, sediments, and tree rings. Each layer of ice and stone holds memory of warmth and cold, stored quietly until someone learns to read it. Even the seasons are part of that pattern. When the northern hemisphere tilts toward the sun, summer comes not because we move closer, but because light hits the surface more directly. The distance barely changes. It's the angle that matters, the way sunlight spreads across the curve. That same tilt gives the southern hemisphere its winter at the same time. If the planet didn't lean, there would be no seasons at all, just permanent dusk near the poles and steady heat near the equator. The lean of the Earth adds rhythm to the warmth, a gentle pendulum that swings through time. At night, when sunlight is gone, the cold returns almost immediately. Space is an efficient thief of heat. The side facing away from the sun radiates energy into darkness, cooling rapidly. The air chills, dew forms, frost gathers. On worlds without atmosphere like the moon, that temperature drop is extreme, hundreds of degrees in hours. On Earth, air and water soften the transition, holding warmth like memory. When you feel the chill of evening, you're feeling the balance resetting, the planet's reminder that nothing stays still for long. From a cosmic perspective, this balance is rare. Venus, only one orbit closer to the Sun, is trapped in relentless heat. Its clouds reflect much of the sunlight, but the carbon dioxide beneath them locks the energy in. Temperatures there stay around 470 degrees Celsius, day and night, pole to pole. Mars, one orbit farther, lost most of its atmosphere long ago. Its thin air lets warmth escape as quickly as it arrives. The average temperature hovers far below freezing. Between them, Earth keeps the middle ground. That middle is narrow, a ribbon of possibility stretching across the Sun's reach. It's tempting to think of that narrowness as fragile, but it's also a form of resilience. The planet has been struck by asteroids, swept by volcanic winters, and covered in ice from pole to equator. Yet each time, it has returned to balance. The feedback loops of climate, the interaction between air, water, rock and life, act like the system's memory, correcting and restoring over time. It's not perfect, but it's persistent. Even life itself has become part of that balance. Plants draw in carbon dioxide and release oxygen. Animals breathe in oxygen and return carbon dioxide. The chemistry of living things feeds the chemistry of air and ocean. The boundary between biology and environment dissolves. If you could measure the temperature of Earth from space, you'd find it averages just below freezing. The warmth you feel here is local, concentrated near the surface by atmosphere and circulation. That difference, between the cold of space and the comfort of the ground, is small in energy terms but infinite in experience. It's the difference between a world where rivers flow and one where they never could. The warmth and cold also shape time in quiet ways. Ice expands and melts, carving valleys and shaping mountains. Warmth speeds decay and growth. Cold preserves and pauses. Every cycle of freezing and thawing, every storm and drought writes history into the landscape. Over millions of years, these forces sculpt continents as if they were clay. The gentle contrast between heat and cold becomes a slow hand, shaping the surface of the marble we live on. Standing outside on a clear night, you can feel both sides of that balance. The warmth stored in the ground rises through your shoes. The cold of the upper air brushes against your face. Above you, stars shine from regions far colder than any place on Earth, while the faint light of the moon carries reflected sunlight across that distance. Every sensation of temperature you feel is a reminder that you live at the edge of two extremes, the fire of the sun and the vacuum of space. As the solar system stretches outward from this balance, warmth fades faster than distance suggests. Light weakens by the square of the distance, double the distance from the sun, and the heat falls to a quarter. Beyond Mars, beyond the asteroid belt, the outer worlds exist in a permanent dusk, where sunlight becomes a distant promise instead of a daily certainty. The line between warmth and cold is invisible, but the consequences of crossing it are immense. It marks the point where ice begins to dominate, where energy becomes scarce, and where worlds sleep under layers of frost. That boundary isn't just physical, it's symbolic. It separates the familiar from the foreign, the worlds that could be like ours from those that never will be. It's the zone that defines what kind of planet Earth is, what kind of life can exist, and what kind of solar system we belong to. When we look outward from here, we're looking from the middle ground, from a place where opposites coexist without destroying each other. Warmth and cold, light and dark, energy and stillness, all balanced in one fragile orbit. The sun sits at the centre of everything we've been describing, not just as a light in the sky, but as the engine that holds the solar system together. Every orbit, every reflection, every faint glimmer on the edge of darkness begins with it. When you think about how small Earth is, it's only fair to consider what we circle, what this marble depends on every second of its existence. The sun is not simply large, it is the measure of large. It dominates not through aggression, but through consistency. It pulls and warms and steadies without pause. From the surface of Earth, it feels like an ordinary thing, rising and setting with dependable rhythm. We've watched it so long that it feels almost familiar, something safe enough to build our days around. But that comfort hides a scale so vast it's almost impossible to visualize. The Sun's diameter is about 109 times that of Earth. You could line up more than 1 million of our worlds inside it, and they'd still not fill the space. It's a sphere of plasma, not a solid object. Its light a product of nuclear fusion in its core, where hydrogen atoms merge into helium. In that process, matter transforms directly into energy, released as light and heat. Every second, the Sun converts 4 million tons of its own mass into pure energy. Every second, it shines with power beyond comprehension, and yet it has been doing so for more than 4.5 billion years. To the naked eye, the Sun seems calm, a bright circle with smooth edges. But through observation, we know that its surface is restless, alive with motion. The visible layer, called the photosphere, ripples like boiling water. Sunspots, dark, cooler regions caused by magnetic activity, form and dissolve over days and weeks. Loops of plasma, called prominences, arc out into space, held by magnetic fields, sometimes collapsing in bursts of energy called solar flares. These flares release particles that stream across the solar system, carried by the solar wind. The wind never stops. It extends far beyond the outer planets, creating a bubble called the heliosphere that marks the true edge of the Sun's influence. Even in the cold of interstellar space, traces of that wind can still be felt. The light that reaches Earth is only a fraction of what the Sun emits, but it's enough. Our planet receives just the right amount of energy to stay balanced between freezing and burning. That balance isn't static. It's maintained by the atmosphere, the tilt, and the distance that we happen to orbit. The Sun doesn't aim its warmth at us specifically. It radiates in all directions, indifferent and even. We are simply positioned at the right distance to make use of it. If Earth were a little closer, water would evaporate into permanent vapour. A little farther, and it would freeze into lifeless ice. Our orbit lies in the thin zone where liquid water can exist, where light can feed plants and keep air in motion. The phrase Goldilocks zone may sound casual, but it describes the narrow strip of probability in which everything we know unfolds. Beyond physics, there's something deeply human in how we respond to the Sun. Civilizations have always seen it as more than a star. In every culture, it becomes symbol and measure, timekeeper and deity, the point from which the day begins and life continues. The Sun was our first clock, our first calendar, our first certainty. Long before we knew what fusion meant, we knew its warmth meant survival. Its absence meant death. When ancient people tracked its rise and fall with stones, they were marking not worship but dependence. We still depend on it, only now through satellites and data rather than prayer. If you imagine floating somewhere between Earth and the Sun, halfway between marble and fire, the view would be both comforting and terrifying. The Sun would fill most of your vision, a blinding sphere radiating in gold and white. You would feel no heat directly, space is too empty to carry it, but you would know that any object facing that light would burn instantly. The Sun's energy travels as radiation, invisible waves of photons that spread outward until they meet something solid enough to absorb them. Every glint off a ring, every dawn on a moon, every bit of light caught in your eye comes from that same stream of photons. The space between the Sun and the planets is measured in light minutes, not kilometers, because ordinary numbers become meaningless. It takes a little more than 8 minutes for sunlight to reach Earth. For Mars, it's about 13, Jupiter, 43. By the time that light reaches Neptune, it has been travelling for more than 4 hours. The solar system is not a space of immediate communication. Everything happens with delay, even light itself. What you see when you look at the Sun is not the present, it's the past, 8 minutes old. What it looks like now, you won't see until the next moment arrives. That delay is small, but it's a reminder that everything in space is a record of something that already happened. The sun's gravity defines the structure of our system. Every planet moves in response to it, not as objects thrown into space, but as bodies falling forever around it. That balance between falling and moving sideways is what creates orbit. Without the sun's pull, the planets would drift away in straight lines, disappearing into cold darkness. Without their sideways motion, they would plunge into the fire. Together, those forces create harmony, motion that looks eternal even though it slowly changes over time. The orbits stretch and wobble, planets tug at each other, but the system holds. For billions of years, it has held. Even beyond light and gravity, the sun's influence shapes what kind of matter can exist in different regions. Close to it, only metals and rock can withstand the heat, forming the small, dense inner planets. Farther out, where it's cooler, gases and ice can condense, giving birth to the giants. The sun is both sculptor and anchor, setting the rules of what can be. It doesn't choose, it simply radiates, and from that steady emission, everything else takes form. From Earth's surface, we rarely think about its scale. The sun seems small enough to cover with a hand just another part of the sky, but its mass accounts for 99.8% of the total mass of the solar system. Every comet, every asteroid, every world, including our own, together make up less than 1% of what the sun holds. We live not near it, but within it, inside the sphere of its influence. Even the light that fills your room, the gentle warmth on your skin, is part of that reach. There's a quiet irony in calling it gentle. The sun is not gentle in any human sense. It's a nuclear furnace roaring without sound. Yet from this distance, its violence becomes comfort. The same flares that could scorch an unprotected world are filtered into soft warmth and daylight here. Its storms, though they send bursts of radiation through space, become auroras on Earth. Curtains of colour dancing at the poles. The solar wind that tears through the void becomes a whisper against the magnetic field that shields our atmosphere. The scale of danger turns into the experience of beauty. Every living thing on Earth carries a trace of the sun, the energy that drives metabolism, movement, growth. All of it originates there. Even the fossil fuels buried in rock are ancient sunlight stored in chemical form. Plants capture photons and lock them into sugars. Animals consume those sugars and continue the cycle. Every heartbeat, every thought, every moment of life is powered by energy that began in the heart of the sun millions of years ago. It's not poetic exaggeration. It's a physical fact. We are, in the most literal sense, made of sunlight slowed down. As powerful as it is, the sun is finite. It's roughly halfway through its main life. In about 5 billion years, it will exhaust the hydrogen in its core and begin burning helium. When that happens, it will expand into a red giant, swallowing Mercury and Venus, perhaps even reaching Earth's orbit. The marble we live on will be reduced to dust, its elements scattered into the same space from which it once formed. Long before that day comes, the sun will have changed enough to alter our climate, making Earth too hot for life as we know it. The timeline sounds immense, but on cosmic scales it's only a chapter. The sun will end as all stars do, by returning its matter to the galaxy, seeding the next generation of stars and planets. In that long view, the sun is not just a light source, but a link. Its energy connects us to the beginning of the universe. The hydrogen it burns was created in the first minutes after the Big Bang. The heavier elements that make up the planets, the rocks, and our bodies came from earlier stars that exploded long before our sun existed. The warmth we feel is ancient. The cycle of matter and energy that began billions of years ago continues quietly every time light touches Earth. To call it dominion is to acknowledge its reach, but also its restraint. The sun rules by presence, not by will. It doesn't command, it sustains. Planets do not obey through intention, but through inevitability. The pull of gravity, the flow of light, the shaping of orbits. These are not choices but the structure of what is. And within that structure, Earth drifts, small and fortunate, warm just enough to hold oceans and life. As the light from the sun travels outward, it weakens, but it never stops. Beyond the outer planets, it still moves, faint and constant, marking the edge of its reign. There, at the limits of the solar system, the warmth becomes memory. The photons so spread out that they can't heat anything but still define the space we call home. That's where the solar wind meets the cold breath of interstellar space, where our star's influence finally ends and the next begins. From that edge, if you looked back, the sun would no longer be a blinding disk. It would be just another star among billions, slightly brighter than most but not special in appearance. Yet for us it's everything. The origin of our warmth, our time, our rhythm of days. It's the centre not because we placed it there, but because without it there would be no we to imagine centres at all. Light is the only constant that lets us measure the universe with any clarity. Everything else changes: speed, position, gravity, motion. But light keeps a single rule. It moves through empty space at 300,000 kilometers per second, a velocity so immense that it seems infinite until you start to measure it across the kind of distances the solar system contains. Only then does the vastness begin to show itself, because even something that fast begins to take time. Light, for all its speed, has to travel, and the travel reveals scale in a way no other measurement can. Every beam of sunlight that reaches Earth began in the sun's core, where hydrogen atoms fuse and release energy that struggles upward through dense plasma. It can take hundreds of thousands of years for that energy to reach the surface, absorbed and re-emitted countless times. Once it escapes into space, the same light that took eons to emerge crosses the distance between the Sun and Earth in 8 minutes and 20 seconds. That delay is small enough to ignore in daily life, but it is proof that we live inside a measurable span, not an instant. The daylight you see is not the present moment of the sun, but a record of where it was 8 minutes ago. The same pattern stretches across the solar system. To reach Mercury, sunlight needs a little more than 3 minutes. To reach Mars, about 13. Saturn, an hour and a quarter. Neptune, more than 4 hours. Even at light speed, the solar system is not small enough to cross in a heartbeat. The outer edges are defined by the time it takes light to arrive. That delay is the quiet clockwork of our star's domain. When spacecraft send signals back to Earth, that clock becomes real in a way that no imagination can soften. The Voyager probes, now more than 20 billion kilometers away, take nearly 20 hours to send a single radio message home. When engineers give them commands, they must wait the same amount of time for a reply. Each conversation spans almost 2 Earth days. The spacecraft and their creators talk across a void so wide that light itself becomes slow. The connection still works only because the rules of physics are patient. Distances like these make kilometers almost useless as a concept. Astronomers use light as the unit instead. A light second, a light minute, a light hour. Each one a slice of space measured by how far a photon can go. The next step is the light year. The distance light travels in a full year, about 9.5 trillion kilometers. It sounds excessive, but when you leave the solar system, it becomes the only measure that fits. The nearest star beyond the Sun, Proxima Centauri, is a little more than 4 light years away. That means its light, visible tonight if you knew where to look, began its journey before the last leap year on Earth. When you see it, you see the past. That same idea applies to everything you can see in the night sky. The farther away something is, the older the light you're receiving. The moon shines with light that left the sun 8 minutes ago and took 1 more second to reflect back. When you look at Jupiter through a telescope, you see it as it was 40 minutes ago. The stars you trace into constellations shine with light that left them decades or centuries ago. Some of them might already have changed, burned out or exploded, but you will not know until their light carries the news. The universe from where we stand is a collection of delayed messages arriving continuously. This delay does something strange to our sense of size. We are used to thinking of space as an expanse of things spread out, but it is also an expanse of times overlapping. When you look into the night, you're not seeing one moment. You're seeing thousands of moments layered together. The solar system itself is a kind of time machine. Each orbit is a delay between emission and reflection, between what is and what was. Earth's own image, if seen from the outer planets, would be several hours old. If someone looked back from Neptune right now, they would see the Earth as it was 4 hours ago, with storms and daylight positioned as they used to be, not as they are. It's difficult for the human mind to hold that idea. We are built to live in the immediate. Our senses evolved for distances we could walk, climb, or cross in a day. The idea that a beam of light takes hours to reach a neighbour planet, or years to cross the gap between stars, stretches our intuition until it snaps. That's why astronomers often build scale models, to turn the intangible into something we can grasp. If the sun were a large lamp in the centre of a city and Earth were a pea 12 metres away, Neptune would be nearly half a kilometre out, and the nearest star would sit thousands of kilometres beyond the city's edge. Even then, the comparison fails to express what the empty space between them feels like. Most of the solar system is void. The planets occupy only a tiny fraction of the available space. The rest is filled with radiation, dust, and the invisible flow of the solar wind. The nearest objects are separated by millions or billions of kilometres of nothing, but through that nothing light travels flawlessly, carrying warmth, colour, and information. It is the only thing that makes the darkness visible. The delay of light also defines what we can know about our place. Astronomers use it to map distance, brightness, and motion. By watching how light shifts and stretches as it moves, they can tell whether a planet is moving closer or farther away, how fast galaxies drift, and how space itself expands. The redshift of distant galaxies, the lengthening of their light into longer, redder wavelengths, is the evidence that the universe is growing, that everything is moving apart. That idea was discovered not through rockets or travel, but through light, the quiet messenger that crosses every boundary. Closer to home, light gives us the rhythm of time itself. We set clocks by the way Earth turns in its glow, mark calendars by the way the planet orbits the source. The same light that grows crops and guides migrations also measures seconds in atomic time. It links biology to physics without any visible effort. The warmth that wakes you in the morning and the starlight that reaches a telescope at night are points on the same spectrum, scaled only by distance. There's a comfort in that constancy. Even when storms on the sun send waves of charged particles through the solar wind, even when magnetic fields twist and release flares, the average output remains steady. The brightness barely varies. For a star, the sun is unusually calm, which may be one reason Earth has remained stable for so long. The light that crosses space does so predictably, a river of photons that never falters. Without that reliability, climates would shift unpredictably, seasons would dissolve, and the thin equilibrium between warmth and cold would break. When light leaves the sun, it travels outward in every direction. Most of it will never strike anything. It will move on forever, growing fainter as it spreads. Some of those stray photons will pass between the outer planets and keep going until they escape the solar system entirely. They will move for thousands of years before brushing past another star or being absorbed by dust. The energy that began as fusion in the sun's heart will end as scattered traces in interstellar space, its journey unfinished but continuous. The solar system is only a brief stop on that path. For spacecraft like Voyager and Pioneer, now coasting beyond the orbit of the last planets, sunlight is already weak. The sun looks like an unusually bright star, no longer the blazing centre we know. The power of its light there is less than 1,000th of what reaches Earth. Beyond that point, solar panels fail to provide energy, and only nuclear batteries keep instruments alive. The time it takes for light to reach those probes and return doubles every few months as they drift farther. Eventually communication will end, not because of failure, but because distance will make the delay endless. The last signals will fade into the same static that fills all of space. When we talk about cosmic distances, it's easy to get lost in the numbers and forget what they mean. Each measure is a reminder of how far the familiar extends before it disappears. Between the inner planets, we can still imagine travel, months to Mars, years to Jupiter. But beyond that, distance becomes duration, not in months or years, but in generations. The nearest star system, Alpha Centauri, is about 40 trillion kilometers away. With our fastest spacecraft, it would take more than 70,000 years to get there. Light will always outrun us, carrying the message of our presence long after we're gone. And yet, for all the scale and delay, light connects everything. It links the sun to the outermost dust grain in the Oort cloud. It links Earth's surface to the eyes that look at the sky. It is both messenger and boundary, the one phenomenon that moves freely through the spaces between worlds. When we think about distance, we're really thinking about how far light has gone, how much of the past is still visible, and how much of the future is waiting to be seen. Even now, every star above you is a map of distance written in brightness and colour. Blue light means heat and youth. Red light means age and retreat. The Milky Way, the faint band across the night, is the combined glow of billions of stars whose light has travelled tens of thousands of years to reach us. When you see it, you're seeing the galaxy's memory. The photons entering your eyes tonight began their journey long before the first humans existed. The solar system is small by comparison, a tiny stage inside a much larger theatre of light and time. Earth's orbit, vast to us, is barely a fraction of a single pixel on the galactic scale. The distance to the outer planets, the width of the entire system, is nothing compared to the span between stars. But even here in this small corner, the principles are the same. Light leaves, travels and returns, marking distance with delay, turning space into a continuum of past and present. When you look at the sky at dusk and watch the first stars appear, you are seeing across unimaginable distances, but also across time. The light that outlines your world and the light that glimmers from those distant suns are parts of the same story. One warms, the other informs, and both move endlessly. The small blue planet you live on, the one circling quietly in the sun's gentle dominion, is a point along that flow. From far enough away, Earth is smaller than thought can comfortably picture. The colours and continents vanish first, then the glint of atmosphere, then even the faint shimmer of reflected light. What remains is not a sphere or a marble or even a dot. It's less than that. A dust grain hanging in a shaft of sunlight. There are no details left to see, only existence itself. A fleck of matter in a volume so vast that every analogy collapses before it finishes. This is the view from the outer solar system, where distance turns into silence and scale no longer fits into language. It's the view that Voyager 1 captured in 1990, when engineers turned the spacecraft's camera back toward the inner system one last time. The image became known as the pale blue dot. In that frame, Earth occupies less than a pixel, a single bluish spark among bands of scattered light. Everything we have ever known exists inside that pixel. The photograph was taken from more than 6 billion kilometers away, a place where the sun is just another bright star. Light took more than 5 hours to travel from the spacecraft back to Earth, so the image is not even a picture of a moment. It's a message delayed by distance, a memory returning from the edge. That delay somehow makes it more honest. You can't see nations, cities, wars, or oceans. There's only a point of colour, small enough to hide behind a mote of dust on your screen, and yet it contains the entire history of the world. Every language, every life, every idea that ever rose and vanished. It's strange to think that this dust grain outweighs its appearance. Earth holds more mass than every living thing in the solar system combined, but compared to the sun, It's nothing at all, less than a fraction of 1% of the system's total mass. The Sun's gravity defines everything. Earth's gravity defines almost nothing beyond the Moon and the bits of debris that follow it. Our planet is not even the largest of the rocky worlds. It's just the one where conditions balance long enough for complexity to unfold. Its smallness is not a flaw, but a feature. The size at which water can stay liquid, an atmosphere can stay bound. When you try to imagine the solar system by size, the picture distorts easily. We often draw the planets close together, lined up neatly for clarity. In truth, the space between them is enormous. If the Sun were the size of a doorway, Earth would be smaller than a coin and more than 10 meters away. Neptune would orbit hundreds of meters farther still. The solar system's matter, all the planets, moons and asteroids, makes up less than 1,000th of 1% of its total volume. The rest is emptiness, crossed only by sunlight and dust. And that dust is what connects everything. It floats through space, scattered by comets and collisions, particles smaller than smoke drifting between orbits. Every meteor that burns in the night sky, every faint trail you see for a second before it fades, is a piece of that interplanetary dust falling home. Each grain carries a story from elsewhere, a fragment of asteroid, a sliver of ice from the outer belt, a molecule of carbon that might once have been part of a planet forming and breaking apart. Over millions of years, those grains settle on Earth's surface, adding layers invisible but real. You breathe some of that dust. It mixes into soil and water. In that sense, Earth is never entirely separate. It is part of a circulation of material that links every world in the system, a single ongoing exchange of matter across space. The atmosphere itself is another form of dust collection. Tiny particles drifting in from space join those lifted from deserts, carried from volcanic eruptions, or created by life itself. They scatter light, shape clouds, and seed rain. The very colour of the sky is the result of sunlight meeting dust and air molecules. Without them, the sky would be black even at noon. Every shade of blue is a negotiation between light and matter, between the emptiness outside and the density of home. Thinking of Earth as a dust grain can feel diminishing at first. The mind resists the idea that something so full of experience could be so small. But smallness here is not the same as insignificance. The dust grain is where complexity hides. If you look at a real grain of dust under a microscope, you'll see structure, detail, irregularities, tiny landscapes invisible from a distance. The same is true for Earth. Zooming out removes that structure, but zooming in restores it. Oceans, forests, storms, and cities are all patterns written on a surface too small to see from space, but vast enough to live entire histories upon. The scale of meaning doesn't match the scale of size. This is one of the lessons that space travel revealed most clearly. Before we saw Earth from beyond it, we imagined boundaries, separations, vast differences between one place and another. From orbit, those divisions disappear. From millions of kilometers away, they cease to exist. The planet looks whole because it is whole. The atmosphere that shields one continent shields them all. The sunlight that feeds one ocean feeds every other. The gravity that holds a mountain range in place also holds the tides that rise and fall on the opposite side of the world. The dust grain is unified not by belief but by physics. Within that unity, the scale of life becomes astonishing. The thin layer of biosphere where all living things exist, roughly from the deepest ocean trenches to the upper atmosphere, is no thicker relative to the planet than the coat of varnish on a globe. And yet within that layer, matter has organized itself into forms capable of thought, movement, and curiosity. The atoms in your body were once parts of ancient stars, scattered into space by explosions billions of years before the sun existed. They drifted as cosmic dust until gravity gathered them again, forming new worlds, new chemistry, and eventually you. To think of Earth as a dust grain is to realise that we are part of the same process. The planet itself is a collection of star remnants held together just long enough for consciousness to arise. Viewed this way, the smallness becomes a kind of grace. Immensity provides context, but the dust grain provides intimacy. The vastness of the solar system allows the conditions for stability. The smallness of Earth allows the conditions for complexity. Planets larger than ours become gas giants, their surfaces lost beneath dense atmospheres. Planets smaller than ours lose their air, their water, their chance to sustain life. Somewhere between those extremes sits Earth, balanced once again between warmth and cold, between emptiness and matter. If you could drift outside the solar system and look back, you wouldn't see the planets at all. The sun would appear as a star of moderate brightness, and around it, nothing obvious. The space between worlds is too large, the light too faint. The dust that fills those regions would be invisible to the naked eye, though it would still be there, reflecting a faint glow known as zodiacal light. Earth would be hidden within it, a mote lost in a beam. That realization isn't humbling in the way people sometimes describe it. It's clarifying. It shows the scale of the stage we occupy and the fragility of the conditions we depend on. In the end, the word dust doesn't mean lifeless. Cosmic dust is the raw material of creation. Stars form when clouds of it collapse under their own gravity. Planets condense from the leftovers. The same particles that drift between worlds will someday gather again into new suns and new systems. The Earth itself is temporary in that cycle, a form that will eventually disperse. Its atoms return to the same interstellar medium from which they came. The dust grain called home is not permanent, but it is part of an unbroken chain of transformation. On this grain, light and shadow alternate in endless rhythm. The side facing the sun glows blue and white, alive with weather and reflection. The side turned away slips into night, illuminated only by the pale light of the moon. As the planet rotates, day and night trade places, a pattern that has persisted for billions of turns. That movement defines the pace of life here. Seasons, tides, sleep and growth all emerge from the spin of a dust grain around its star. The scale may be cosmic, but the rhythm is personal, felt in every breath. If you could hold that grain between your fingers, the instinct would be to protect it. It would seem too delicate, too intricate to risk. That instinct is correct. The thin film of atmosphere, the balance of heat and cold, the fragile networks of life, all depend on a narrow range of conditions. A small change in any of them could unravel the whole pattern. The awareness of that fragility is not a burden, it's a form of attention. Knowing how small the planet is makes its continuity more precious. Out beyond the orbit of Neptune, the sun's warmth is little more than memory, but its light still reaches. Each planet, each moon, each shard of ice and rock reflects a portion of that light back toward the centre. Earth, tiny as it is, shines brightest among them, not because it is large or close, but because of water, air, and cloud, all materials that scatter light efficiently. To an observer far away, it would shimmer like a jewel caught in motion. They would see the dust grain not as an insignificant speck, but as a point of beauty in the dark. The idea of home changes when you understand this. Home is not just a place on the surface, or even the planet itself. It's the orbit, the sunlight, the balance, the shared space that sustains everything here. The dust grain called Earth is part of a larger system that begins with the sun and ends nowhere in particular. It drifts, turns, and glows, carrying life through a vacuum that would kill it in seconds without protection. That contrast, the fragility of the world against the indifference of space, makes the smallness meaningful. As the view widens farther still, the solar system starts to lose its edges. The space between the planets becomes the space between stars. The light from our sun merges with the light of others. The dust grain called home becomes one among countless others, each circling its own source of warmth. It's there, among those countless points, that the next question waits quietly. If the solar system itself is only one grain in the cosmic dust of the galaxy, then where does its edge truly lie, and how far does home actually reach? Every system, no matter how vast, has limits, though in space they are never marked by walls or edges. The solar system looks endless from within, but it does have a boundary, defined not by sight but by influence, by the point where the sun's power fades and other stars begin to matter. These are invisible boundaries, felt rather than seen, measured not in kilometres but in effects. How far the solar wind can push, how long gravity can hold, how much light remains bright enough to matter. Earth, tiny and bright, lies deep inside that sphere of influence, safe within the reach of the sun's warmth and pull. Out here, near the edge, the sun is no longer the light of day but a single point among many. The first boundary is one of warmth. It's the place where sunlight becomes too faint to heat anything directly, where ice can remain solid forever, and energy arrives more as idea than as force. That region begins beyond Neptune, where the last of the major planets circles in slow, silent orbit. Out there, the sun's light takes hours to arrive, and is hundreds of times weaker than what reaches Earth. The temperature drops so low that gases like nitrogen and methane turn to frost. Yet the light still travels, and its pull still binds. The invisible boundary of heat does not stop life. It simply stops movement, freezing worlds in time. Beyond Neptune lies the Kuiper Belt, a wide ring of icy debris extending billions of kilometres outward. It's the solar system's outer construction zone, full of remnants that never merged into planets. The bodies there are small, irregular and ancient, leftovers from the beginning, untouched by the heat of formation. Pluto lives here, along with Haumea, Makemake and Eris, worlds that orbit the sun at vast distances, following paths stretched and tilted. They are cold enough that sunlight reflects off frozen methane and nitrogen like metal. From their surfaces, the sun looks like a distant star, bright enough to cast shadows but too small to warm a hand. These worlds mark the first soft edge of the solar system, the zone where planets end and remnants begin. The second boundary is one of gravity. The sun's mass holds everything in orbit, but its grip weakens with distance. Beyond a certain point, other stars begin to tug with equal subtlety. That region, known as the Oort cloud, is a sphere of icy bodies extending perhaps a light year from the sun. None of those objects have ever been seen directly. Their existence is inferred from the long-period comets that occasionally visit the inner system, falling inward after being disturbed by passing stars or the galactic tide. When those comets sweep through our skies, their glowing tails remind us that the solar system is not a closed bubble, but a space exposed to outside influence. Each one is a message from the edge, proof that our home system blends seamlessly into the interstellar medium beyond. The third boundary is made by the solar wind. The sun constantly emits a stream of charged particles, protons, electrons and heavier ions, that rush outward in all directions. Near Earth, the solar wind shapes auroras and interacts with magnetic fields. Farther out it continues, a faint but steady breath filling the solar system. At some distance, that outward flow meets the pressure of particles from other stars. The point where the solar wind slows and finally stops is the heliopause, the true frontier of the sun's domain. It's the place where the solar wind's influence ends and the interstellar medium begins. Voyager 1 crossed that boundary in 2012, followed by Voyager 2 in 2018. They were launched decades earlier in 1977 to explore the outer planets. After their flybys, they kept going, carried forward by momentum alone. As they moved past Neptune's orbit, their instruments began to detect changes. The density of particles around them shifted, magnetic fields twisted, and the direction of charged cosmic rays altered. When those readings confirmed that the solar wind had dropped away, scientists realized the spacecraft had entered interstellar space. It was the first time anything made by humans had left the heliosphere entirely. Voyager 1 is now more than 24 billion kilometers from Earth, still sending faint signals home. Each bit of data it transmits takes more than 22 hours to reach us. Even at a light speed, communication is no longer immediate. To imagine that distance, picture the solar system as a single city. Earth would orbit within its downtown, busy and bright. The gas giants would be the suburbs, vast and open. The Kuiper belt would stretch into the countryside, quiet and cold. And the Oort cloud would be the far edge of the province, a place where streetlights fade and wilderness begins. Beyond that lies the next city, the nearest star system, Alpha Centauri, separated by emptiness so immense that even light takes 4 years to cross it. That gap between cities is not empty of everything, though. It's filled with thin gas, magnetic fields, and stray dust, the material of the galaxy itself. The sun moves through it like a ship through fog, carrying its family of planets inside a bubble of influence. These boundaries are not fixed lines. The heliosphere changes shape as the solar wind fluctuates with the sun's activity cycle. Every 11 years, when sunspots and flares peak, the wind grows stronger and pushes farther out. When the sun quiets, the bubble contracts. The Oort cloud, too, is a region of probability, its size determined by gravity that fades gradually rather than abruptly. The edges of the solar system are soft, elastic and responsive. They breathe with the star they surround. Even within the inner system, invisible boundaries define space. Earth's magnetic field forms a shield that protects it from the solar wind, shaping a magnetosphere that stretches far beyond the atmosphere. The boundary between day and night, the terminator line, moves continuously as the planet spins, dividing warmth from cold in a seamless rotation. Each orbit, each layer, each flow of air or particle marks another frontier that cannot be seen but can always be felt. The solar system is full of such thresholds, places where one influence ends and another begins. At its heart, this structure is not chaos but order. The invisible boundaries give shape to the system's stability. Without them, particles would drift without pattern, comets would wander aimlessly, and planets might lose their paths. Gravity, magnetism, and radiation are the threads that weave this structure together, invisible but firm. They define space without enclosing it, maintaining balance across billions of kilometers. When you think about those edges, the idea of inside and outside becomes less certain. The solar system is not an isolated bubble in a vacuum. It's a gradient, a transition between one region of the galaxy and the next. The sun moves through the Milky Way at about 200 kilometers per second, carrying its planets with it like a caravan of light. Over millions of years, it passes through different regions of interstellar gas and dust. Each encounter changes the shape of the heliosphere slightly, sometimes shrinking it, sometimes swelling it. The system breathes not just with the sun, but with the galaxy itself. The boundaries also shape what we can observe. Telescopes capture light that has travelled across those regions, but instruments detect particles and fields directly. When Voyager crossed the heliopause, the data it sent back was more than symbolic. It was a measurement of transition. Inside the heliosphere, the solar wind dominates. Outside, the density of cosmic rays increases, coming from distant supernovae and other stars. The readings told us we had truly left the sun's domain. Yet even beyond that line, the sun's gravity still rules. It will hold its outermost comets for millions of years more. There's something poetic in the idea that the system's edge is defined not by what we see, but by what we feel. The light fades gradually, but the pull remains. The sun's warmth may no longer reach, but its gravity never stops entirely. The invisible boundaries blend into one another, like the fading tones of a long echo. It's a structure built not of walls, but of transitions. From this perspective, Earth's place inside feels both protected and temporary. Protected because we live far within the sun's warmth and shield, close enough for light to nurture, but distant enough for comfort. Temporary because the solar system itself drifts through the galaxy, its boundaries shifting, its position changing. The space we inhabit now will not be the same in 1,000,000 years. We move not just around the sun, but through a cosmic sea that reshapes the edges of home. When you look at the night sky, those invisible boundaries define what you can and cannot see. The stars beyond are members of other systems, bound by their own centres, their own winds and clouds. Between them lies the interstellar medium, the space that connects all suns. The Milky Way is a web of these overlapping influences, stars and systems nested within one another's reach. The solar system's invisible edges are not limits, but overlaps, the regions where our light and others meet and mix. From the vantage of deep space, when even the sun becomes just another point of light, the planets that once seemed enormous shrink into anonymity. They become faint echoes of themselves, moving in silence around a star no one else can see without help. The farther you drift, the clearer the truth becomes. Our solar system, for all its grandeur, is small, and within it, Earth is smaller still. It is a minor sphere orbiting a modest star, itself one among hundreds of billions in a galaxy so wide that its light takes 100,000 years to cross. The phrase "tiny among titans" fits not as poetry, but as measurement. Every layer of perspective reduces us further, until what once felt infinite, the sky, the sea, the horizon, becomes an invisible fraction of something larger beyond imagining. The Voyagers were the first messengers to show this perspective with more than theory. After passing the outer planets, Voyager 1 turned its camera backward to capture that image of Earth as the pale blue dot. From that distance, 6 billion kilometers away, Earth fit comfortably inside a single pixel. Every ocean, every city, every word spoken or written, all condensed into one faint point of scattered light. The spacecraft continued onward, eventually leaving the heliosphere entirely, passing through the invisible boundaries where the solar wind fades and the interstellar medium begins. From there, even the sun was no longer overwhelming. It was just another bright star in a sky filled with others. If you were to stand in Voyager's place, suspended beyond the reach of the last planet's orbit, the scene around you would not resemble the neat diagrams in textbooks. There would be no glowing trails or clustered spheres. The planets would be invisible to the naked eye, each one hidden by distance. The sun would dominate the sky, yes, but not as a disk. It would appear as a bright, sharp point, much like the other stars, though a little more intense. You could point toward where Earth should be and still see nothing. In a field of light, our home would be smaller than a grain of dust, smaller than any distinction that matters to the human eye. The space between stars, for all its emptiness, defines the shape of everything we know. The nearest star, Proxima Centauri, sits more than 4 light-years away. The light leaving it tonight won't reach us until mid-decade in the next presidential term. The gap between that star and the sun is so large that if you shrank the sun to the size of a tennis ball, Proxima would be another tennis ball more than 7,000 kilometers away. Every system in the galaxy floats like that, isolated, surrounded by distance that cannot be crossed quickly. Within those gaps drift titans, stars larger than the sun, denser remnants of those that have already died, black holes so massive that even light cannot escape them. Against them, the sun and its planets vanish completely. Consider a comparison that astronomers sometimes use to communicate the gulf of scale. If you place the entire solar system out to the orbit of Neptune, inside the sphere of a basketball, the Milky Way galaxy would still be larger than Earth itself compared to that ball. The number of stars within it surpasses comprehension. There are hot blue giants that burn millions of times brighter than the sun, collapsing in a few million years. Red dwarfs that burn dimly but can survive for trillions. There are neutron stars only a few kilometers wide but with masses greater than the sun. their density so extreme that a spoonful would weigh as much as a mountain, and there are black holes, true titans, where mass becomes pure gravity, bending space and time. Next to those extremes, the Sun is modest, and Earth clinging to its orbit is microscopic. Yet even modest stars can have empires. Around each point of the light you see in the sky, there may be planets, moons, and rings. Many of them have been detected now. Thousands of exoplanets, ranging from worlds smaller than Mercury to those larger than Jupiter. Some orbit so close to their stars that a year lasts only a day. Others circle so far away that their sunlight is dimmer than our moonlight. The diversity is staggering, and it places our system in context. One of countless, unremarkable in size but miraculous in consequence. This understanding doesn't erase the feeling of significance, it changes it. Being small doesn't make us irrelevant. It means that the universe is large enough for possibility. The same physics that lets supergiant stars fuse heavy elements in their cores also allows planets like ours to exist, covered in water and life. The giants forge, the small ones sustain. Each scale plays its part in the larger pattern. In that way, being tiny among titans is not a deficit but a role, one that completes the story rather than diminishing it. When the Voyagers sent back their final photographs, they showed more than distance, they showed context. Each planet appeared as a tiny point of light scattered along beams of sunlight reflected within the camera lens. Jupiter, Saturn, Uranus, Neptune, each a speck against the black. The entire family of worlds fit within the width of a single frame. That image carries an idea we still struggle to grasp. We live in a system that, compared to the galaxy, is an island smaller than imagination allows. Beyond it, stars fill the dark like dust. The distances between them are the true measure of cosmic scale, not the sizes of planets or even the brightness of suns. Astronomers often describe stars as main sequence, giant, or dwarf. These are stages of life, not titles of importance. Our Sun sits comfortably in the main sequence, neither young nor old, neither massive nor small. In human terms, it's middle-aged, halfway through its stable burning phase. The giants that outshine it burn faster, ending in explosions that scatter new elements into space. The dwarfs that outlast it will glow faintly for ages after the sun has faded. The galaxy needs all of them. The brief brilliance of the giants to create new matter, the slow constancy of the dwarfs to keep time. Earth, orbiting a modest star, belongs to the slow and stable middle ground, a fortunate position in a universe of extremes. Even among titans there is hierarchy. The Milky Way itself orbits within a cluster of galaxies called the Local Group, which in turn drifts inside a larger structure known as the Virgo supercluster. Beyond that, filaments of galaxies form webs spanning billions of light-years. Each cluster contains hundreds of billions of suns, and between them stretch voids so empty that no particle of matter may exist for entire light-years at a time. The scale grows until words lose traction, until our numbers become only symbols of incomprehension. Against that scale, the entire solar system is less than a mote suspended in a sunbeam, and yet, for all its minuteness, the solar system remains a complete system, self-contained, ordered, alive with motion. The orbits of the planets trace precise paths that have endured for billions of years. Gravity holds, light flows, and the delicate balance continues. In a universe filled with explosions and collapse, stability itself is a kind of rarity. That stability gives smallness meaning. It gives it texture. From another world, say, an observer orbiting one of those titanic stars, the sun would be nothing special. It would blend into the background of the Milky Way, another faint spark in a crowded field. But if that observer had a telescope strong enough to see its planets, they would find something unusual. One of those faint dots would reflect blue light in a way that no other known world does. It would glimmer irregularly, its brightness shifting as clouds and oceans moved. That flicker would betray an atmosphere dense with oxygen and water vapour, conditions that mark it as living. Among all the dust and gas, among all the dead rocks and frozen giants, the smallest world in that view would be the one carrying awareness. That awareness changes everything. The titans, stars, black holes, galaxies are powerful, but they do not know they exist. The dust grain that orbits quietly in their shadow does. From that knowledge comes observation, from observation comes wonder, and from wonder comes meaning. The giants may define the structure of the universe, but the small things define its understanding. We are not separate from the titans. We are their consequence, their reflection in miniature. In the cold clarity of space, Earth is invisible, but its influence reaches farther than its size allows. Radio waves, spacecraft, the faint glint of satellites, these are the signs of presence, the first whisper of awareness expanding outward. Compared to the roar of the cosmos, it's a quiet sound, but it's new. For the first time, a world has begun to speak into the dark. That, more than size or power, is what gives the dust grain its weight. From a distance, Earth looks steady, turning with the same rhythm it has held for billions of years, shining softly under the light of the sun. But up close, stability reveals itself as an illusion, sustained by balance. Every force at work here, the pull of gravity, the pressure of air, the warmth of sunlight, the spin that gives us day and night, is part of a delicate equation that could falter with the smallest shift. We live suspended in that balance, a thin layer of warmth and motion resting between the deep cold of space and the heat of the planet's core. To exist on such a fragile platform is to live on a thread, floating between extremes. The fragility begins with the air we breathe. It feels infinite, stretching from horizon to horizon, yet the entire atmosphere is barely a veil. If Earth were the size of a globe in your hands, that veil would be thinner than a coat of paint. Within that film lies everything, every breath, every sound, every cloud, every storm. It keeps the oceans from boiling, the surface from freezing, and life from vanishing. Above it, the air fades into vacuum so quickly that within minutes of upward travel, you would reach a height where blood would boil unprotected. The boundary between comfort and nothingness is only a few dozen kilometers wide, thinner than the space between cities on a map of the world. Beneath that air lies the ocean, another fragile layer. It seems vast when you stand beside it, endless in all directions. Yet compared to the size of the planet, it's a mere skin of water. The average depth of the sea is less than 4 kilometers. If Earth was smooth, the oceans would cover it in a film barely thicker than dew, and that film contains most of the life on the planet. Tiny plankton drifting near the surface produce much of the oxygen we breathe. Currents circulate warmth from the equator toward the poles, distributing energy, keeping temperatures stable. Without the ocean's constant motion, the planet would swing wildly between heat and cold. Stability depends on this liquid skin, and it depends on the same gravitational pull that holds the moon in place. Tides driven by that pull mix the ocean's layers and keep the chemistry alive. Even the land beneath our feet is not solid in the way we imagine. The crust of the earth, the ground on which we build everything, is only a thin shell floating on molten rock. It shifts constantly, pushed by convection currents from the mantle below. Over time, continents drift, collide, and reshape themselves. Mountains rise and erode, oceans open and close. The surface we call permanent is actually temporary, rearranging itself on a timescale longer than memory but shorter than eternity. The fragility here is hidden in slowness, a movement so gradual that it passes unnoticed until it changes everything. Our orbit itself is another balance. The Earth travels around the Sun at nearly 30 kilometers per second, fast enough to cover the distance from New York to Tokyo in less than a minute. That speed is exactly what keeps us from falling inward. If we slowed by even a fraction of a percent, gravity would begin to pull us closer, raising global temperatures and altering everything from climate to the shape of the day. If we sped up, we would drift outward, losing heat until the seas froze. The same principle applies to the moon. Its distance from Earth increases by a few centimeters each year as tidal forces transfer energy outward. That slow retreat changes the length of our days and stabilizes the planet's tilt. Without the moon's influence, Earth's axis would wobble chaotically, seasons would swing unpredictably, and climates would collapse. The moon's quiet presence keeps our world steady, its motion a silent partnership holding the rhythm of life in place. The planet's internal engine adds another layer of fragility. Deep below the surface, radioactive decay keeps the core molten, driving convection that generates Earth's magnetic field. That invisible field shields the atmosphere from the solar wind, deflecting charged particles that would otherwise strip it away. Mars once had such a field and lost it, along with most of its air. Without that magnetic shield, the solar system would slowly erode us, atom by atom, until the sky thinned and the seas evaporated. Our survival depends on the restless churning of a molten heart thousands of kilometers beneath our feet. Even the temperature of the sun, constant enough to sustain life, fluctuates subtly over time. The solar cycle brings changes in magnetic activity every 11 years, sending waves of radiation that ripple through space. When those waves reach Earth, they influence climate, satellites, power grids, and the shimmering auroras that dance over the poles. The fragility of life here depends not only on what happens on the planet, but also on what happens within the star we orbit. A single solar flare large enough could disrupt the thin technological shell we've built. The satellites, communication systems, and power networks that now serve as the planet's nervous system. Our sense of permanence comes from habit, not from reality. The climate that has allowed civilization to flourish has been unusually stable for the last 12,000 years. In the 4 billion years before that, Earth swung between fire and ice, between volcanic winters and tropical ages. Life adapted, changed and survived, but not always gently. Mass extinctions came and went, each one resetting the balance. The stability we live in now is a rare pause in a long sequence of instability, a brief calm in the planet's deep history. It's easy to forget that fragility when surrounded by comfort. Walls, roofs, cities and technology create the illusion that we've separated ourselves from the planet's raw forces. But those systems depend on the same fragile foundations. A shift in temperature, a rise in sea level, a change in rainfall, all ripple through economies and ecosystems. The line between comfort and collapse is as thin as the atmosphere, as temporary as the calm between storms. Civilization itself is a structure balanced on that thread of stability, and like every natural system, it is not immune to change. Beyond physical fragility lies something subtler, the fragility of awareness. The fact that we can even recognize these balances depends on the continuity of thought, culture, and memory. Our ability to understand the planet, to send probes beyond the solar system, to see the dust grain called home from afar, all of it comes from a chain of learning that began in fragile minds. Ideas are as perishable as life. They survive through preservation, through repetition, through sharing. The knowledge that allows us to grasp our smallness could vanish as easily as an ecosystem if not maintained. Fragility is not only a matter of matter, it is a matter of mind. Still, fragility doesn't mean weakness. The same thinness that makes the atmosphere delicate also makes it dynamic. The same ocean that can flood coasts also buffers heat and carries nutrients across the globe. The same crust that can fracture in earthquakes builds mountains that redirect weather and create habitats. Fragility in nature often means responsiveness, the capacity to change, to adapt, to bend without breaking. Earth's floating balance is not a brittle structure waiting to shatter, but a flexible one adjusting constantly to forces around it. That adaptability has allowed life to persist through impacts, eruptions, and ice ages. If you could look at Earth from space long enough, you'd see that adaptability as motion. Clouds drift, storms spin, ice melts, vegetation shift colour with the seasons. From orbit, it's visible even in time-lapse, a living planet breathing through cycles of light and dark, heat and cold. Fragility and endurance are not opposites here. They are the same process viewed at different scales. The planet looks peaceful from afar because its instability is balanced. Every disturbance becomes part of the pattern, every variation absorbed into the rhythm. When astronauts describe seeing Earth from orbit, they often mention its thinness, its vulnerability. The horizon curves sharply, the atmosphere glows faintly blue, and beyond it there's only blackness. From that distance, the world looks self-contained but also exposed, a bubble of life floating through an ocean of emptiness. The phrase, fragile oasis, comes up often, not as a metaphor but as direct observation. They can see it with their own eyes, the paper-thin barrier that separates everything alive from the vacuum of space. Even so, that fragility holds its own kind of strength. The planet endures not because it is hard, but because it is resilient. It flexes, shifts, and reforms. Life itself amplifies that resilience. Forests absorb carbon, oceans store heat, organisms evolve to fill every niche. The biosphere repairs itself constantly, though not infinitely. It can be damaged, but it can also recover, given time and balance. The challenge for those living within it is to remember that balance is earned, not guaranteed. The phrase floating fragility suggests something precarious, but it also implies grace. Earth doesn't hang in space by accident. Its motion, its orbit, its tilt, its atmosphere, all follow laws that have held for billions of years. Within those laws, fragility becomes the texture of existence. To be alive on this planet is to be part of that delicate continuity, to feel both the danger of imbalance and the wonder of persistence. If we continue to look outward, to measure and understand, we'll see that this fragility is not unique. Every planet, every moon, every star lives within its own limits, sustained by balances that can shift. The difference here is awareness, the ability to notice the balance, to protect it, to reflect upon it. Earth's smallness, its floating fragility, is not a flaw in the design of the solar system. It is its rarest achievement, the place where complexity and consciousness converge. As we drift farther into thought, leaving the familiar warmth of the sun behind, the question changes again. If fragility defines life and awareness, then what happens when we reach the scale where life can no longer endure? Size is one of the simplest things to measure and one of the hardest things to understand. A number can tell you how wide a planet is, how long its orbit lasts, how heavy its mass might be, but it can't capture how that size feels when you try to imagine it. The solar system is made of dimensions so uneven that comparison itself becomes slippery. Between the microscopic world that builds us and the cosmic world that surrounds us lies a ladder of scale with no top and no bottom. At one end, molecules move so small and fast they become invisible. At the other, stars drift so slowly they look still. Somewhere in the middle sits Earth, balanced between immensity and minuteness, where size and wonder overlap. When you first think about the sun, you think of it as enormous, and it is. But that size only carries meaning when you compare it to the space it occupies. The sun could hold 1,000,000 Earths, yet in the solar system it's just one more point orbiting the galactic centre. Jupiter could hold more than 1,000 Earths inside it, but compared to the sun, it's tiny. The entire solar system, out to Neptune's orbit, fits comfortably inside a region of space smaller than a single pixel in most photographs of the Milky Way. Each step upward in scale erases what came before, Earth disappears next to Jupiter. Jupiter disappears next to the Sun disappears next to the galaxy. And then the galaxy itself vanishes inside the pattern of clusters and filaments that stretch across the universe. Every layer of size dissolves into something larger. Yet the human mind has a strange reaction to immensity. It doesn't flatten us, it expands us. The more you understand how small Earth is, the more your sense of awe grows. You realize that to exist at all, to be a part of something so extensive that it can't even fit inside your imagination, is its own kind of miracle. Wonder thrives on proportion, not pride. When you see how vast the Sun's energy output is, how deep the atmosphere of Jupiter reaches, how far light travels between stars, it doesn't make your world meaningless, it makes meaning feel earned. Every time scientists calculate a new measurement, how long it takes for a signal to reach a probe, how bright a star burns, how fast a planet moves, they extend the boundary of scale. The distances become abstractions, but they remain connected to familiar experiences. A single heartbeat is about 1 second. In that time, light travels 300,000 kilometers. That's nearly the distance from Earth to the Moon. The Moon's orbit is a second of light away. The Sun's light takes 500 seconds to reach us. In that same time, your heart beats 500 times, your lungs breathe, your thoughts continue. A heartbeat equals a moon's distance. A few minutes equal the span between Earth and Sun. Size becomes time becomes scale, and wonder becomes the bridge that lets you cross it. From this perspective, even the smallest parts of the solar system grow vast in meaning. A grain of dust drifting near the rings of Saturn follows the same laws of motion as the planets. Its orbit is shaped by gravity, its path altered by sunlight. The same equations that describe the movement of galaxies apply to it. Scale doesn't change the principles, only the context. The universe is democratic in that way. The rules that govern the fall of an apple also govern the arc of a moon. Every object, no matter how large or small, participates in the same structure. That continuity is what turns knowledge into wonder. The realization that simplicity underlies everything that looks complex. When Voyager 1 and 2 were launched, their creators didn't know exactly how far they'd go or what they'd find, only that they would keep travelling outward, measuring and transmitting for as long as they could. They carried small gold records with sounds and images of Earth, music, greetings, diagrams of our place in the galaxy. Those records are now farther from the Sun than any other human object. They drift through space as symbols of perspective. Against the scale of the cosmos, they're nothing more than dust, but the messages etched into them are a form of wonder made solid. A single spacecraft smaller than a bus carries knowledge across billions of kilometers, proof that awareness can leave its origin. If size teaches humility, wonder restores significance. The giants of the solar system are breathtaking, not because they make us feel weak, but because they show us how stability can exist in extremes. Jupiter's storms, Saturn's rings, Neptune's winds. They reveal scale as a language of endurance. Those massive worlds hold together under pressures that would destroy any solid surface. They turn endlessly, resilient through chaos. Their gravity sculpts the orbits of smaller bodies, keeps asteroids in place, and protects Earth from many collisions. Their size serves a function, and that function creates space for smaller worlds to thrive. The giants and the dust grains coexist, each depending on the other in quiet mathematical ways. When you consider that connection deeply, size becomes less about measurement and more about relationship. Earth's smallness is not isolation but integration. It exists in proportion to the rest of the system. Its light reflects enough to be seen but not enough to blind. Its gravity holds oceans without crushing them. Its orbit receives warmth without burning. The world's size defines its character, its possibilities, its fragility. Without being small, it could not be balanced. Without balance, it could not be alive. Wonder, then, is what happens when awareness meets that truth. It's the recognition that there's no right size for meaning. The same feeling arises when you look at the Milky Way through a telescope and when you watch frost forming on a window pane. The scale changes, but the sensation is the same. The boundary between comprehension and awe. That boundary, like everything else in the universe, is invisible and shifting. You reach it, cross it, and realize it only when you feel small and infinite at once. Scientists who study the extremes of scale, particle physicists and cosmologists, often describe a strange symmetry in their work. The smallest structures of matter resemble the larger structures of the cosmos. Atomic orbitals echo the paths of planets. The distribution of galaxies mirrors the patterns of energy in the subatomic vacuum. It's as if the universe repeats its ideas at different magnitudes, weaving the same forms into every level of reality. To understand one scale is to glimpse the others. That echo across size is another kind of wonder, the recognition that the cosmos is consistent, that its complexity arises from repetition. Our place in this pattern is peculiar. We exist at the scale where both directions, toward the small and the vast, are accessible to the mind. We can split atoms and chart galaxies, shrink understanding to quarks or stretch it to clusters. That position is not privilege, it's coincidence. But coincidence can be meaningful when consciousness enters the equation. From this midpoint we can look both inward and outward, connecting the molecular to the cosmic. The wonder lies in seeing both ends of the spectrum at once, in realizing that we are made of particles forged in stars and are capable of studying the stars that forged them. In this balance, size ceases to be hierarchy. The large is not superior to the small. The sun depends on the nuclear reactions of the tiniest particles. The planets depend on the pull of that star. Life depends on the chemistry of carbon, hydrogen, oxygen, all light elements born in the deaths of larger suns. The great and the small are linked, not opposed. Wonder arises from the continuity, from seeing how the universe builds itself layer by layer out of connections that scale seamlessly. When astronauts describe the view of Earth from orbit, they often mention how size disappears as a category. The planet looks both enormous and fragile, both vast and limited. Its horizon curves, its weather moves, its surface glows faintly against black space. The feeling that follows isn't fear of smallness, but amazement at coherence. Everything fits, everything interacts, everything holds. The size of the system doesn't cancel the importance of the individual, it gives it context. If you extend that feeling farther, beyond the solar system the same principle holds. The galaxy, immense as it is, follows the same pattern of motion as the solar system. Stars orbit the centre much as planets orbit the sun. The Milky Way is bound by gravity, its arms shaped by rotation, its light scattered through dust. It's a scaled-up reflection of what we already know, a reminder that every immense thing begins as something small. Wonder isn't the opposite of understanding. It's what happens when understanding reaches its limit. To study the solar system, to measure its distances and compare its sizes, is to move toward that limit. Each discovery pushes comprehension outward until it blurs into awe. The more precisely we describe the vast, the more we feel its mystery. Science doesn't shrink wonder. It sustains it by showing how endless the climb is. There is no top rung, no final measure. Every size reveals another. Earth, the small blue world turning through the dark, remains both the observer and the observed. Its size gives us perspective. Its smallness gives us curiosity. Without that combination, we would never have looked outward at all. The titans may be larger, the distance is immeasurable, but wonder belongs to the scale that can recognize them. And so, as our minds travel beyond the reach of light and warmth, through regions where scale becomes abstraction, we carry that recognition with us. Size no longer limits meaning, it amplifies it. The solar system, the galaxy, the universe, all of it becomes a mirror reflecting back the same truth. The smaller we seem, the greater the wonder becomes. For all the vastness of the solar system, for all the distances that make even light hesitate, we keep returning to the scale we know best, the human one. It's the only scale we can feel. Every measurement we take of the cosmos, every number we assign to a planet or a star is anchored to what fits in our senses. We compare things to what we can hold, what we can see, what we can survive. The universe does not think in meters or minutes. Those are inventions we use to make it comprehensible. The solar system doesn't measure itself, it simply is. The human measure is what turns that into meaning. When we speak of Earth's size, we do so with reference to our own dimensions, the height of mountains, the depth of oceans, the speed of a plane, the reach of sight. The numbers are familiar, but the reality they represent is far beyond what those senses can grasp. The tallest mountain is less than a fraction of the planet's radius. The deepest trench barely scratches the crust. The horizon we see from sea level, that soft curve of blue and grey, is only 5 kilometers away. We're surrounded by scales that exceed us, and yet we interpret them as manageable, because our minds have learned to fold vastness into comparison. That act of folding is what makes understanding possible. Astronomers, when describing cosmic distances, often reduce them to human time, light minutes, light hours, light years. It's not that time and space are the same, but that time is what we understand directly. We can't picture 1 billion kilometers, but we can feel what 8 minutes means. The sunlight on your hand began its journey from the sun before you began your morning routine. The radio signal sent to a probe orbiting Neptune won't arrive until after your dinner. We make sense of scale by turning it into duration, translating distance into the rhythm of our lives. Every number becomes a metaphor, every fact a reflection of what a human can experience. The same pattern applies to the way we perceive motion. Earth spins at over 1,000 kilometers per hour at the equator, yet we feel still because that speed is constant. The planet hurtles around the sun at nearly 30 kilometers per second, and the sun itself drifts through the galaxy at 200 kilometers per second. But our senses measure movement relative to ourselves, not to the void. The human measure filters everything through comfort. When that filter slips, when an earthquake moves the ground or a storm makes the air shake, we remember how small we are against the planet's forces. In those moments, the scale of nature breaks through the scale of habit. Even our maps of the solar system are acts of translation. We can't draw the true distances between planets and keep them on a page, so we compress space to make it fit. Diagrams show the planets lined up neatly, equally spaced, frozen in motion, but the real system is messy and enormous. Between Mars and Jupiter lies a gulf of hundreds of millions of kilometers. Between Neptune and the next star lies emptiness so large that no printed image could contain it. We compress it anyway, because the human mind requires proportion to understand. The measure of the human is not accuracy, it's interpretability. If you look at the earliest drawings of the cosmos, they often place Earth at the centre. That wasn't arrogance as much as necessity. Before telescopes, before instruments, before even the idea of orbit, there was only observation from the ground. The human measure began at eye level. The sun rose and set, the stars turned, the moon waxed and waned. The sky seemed to move around us because that's how perception works. Everything is relative to where you stand. When Copernicus proposed that Earth moved around the sun, it wasn't just a scientific revolution, it was a shift in measure. It meant that our senses could deceive us, that our frame of reference was not absolute. Understanding the cosmos required stepping outside the human measure without losing it. We still use that double vision. On one hand, we measure in meters, seconds, kilograms. On the other, we interpret through metaphor, image, and feeling. The scientific and the sensory overlap. When we say that Jupiter is 11 times wider than Earth, that's a fact. When we imagine standing beneath its swirling clouds, that's translation. Both are necessary. Data alone doesn't create meaning. Meaning comes from how data connects to experience. The human measure is not just the unit, it's the bridge between knowing and feeling. In that sense, the solar system becomes a mirror. Every number we attach to it reflects something about us. Our need for proportion, our instinct to compare, our desire to belong in a structure too large to inhabit physically. We measure distances not just to know how far away things are, but to locate ourselves emotionally within them. When you learn that light from the sun takes 8 minutes to reach Earth, you can feel that delay. It becomes a rhythm, a pulse connecting you to something unimaginably large. The numbers stop being abstract when they echo human tempo. The instruments we've built, the telescopes, probes and sensors, extend that measure outward. They are our borrowed senses. When a spacecraft photographs Saturn's rings, it's our eyes seeing farther. When a spectrometer analyzes sunlight reflected from a moon, it's our tongue tasting distance. The machines translate scale into data, but we translate data back into comprehension. Through them, the human measure expands without ever losing its center. We are still measuring from ourselves outward, from the known to the unknown. The tools grow sharper, the reach longer, but the origin point remains the same. There's an irony in how the smallest things we make, microchips, sensors, delicate instruments, allow us to study the largest things that exist. The exploration of size loops back on itself. Miniature tools reveal enormous truths. The solar system's immensity can only be mapped by devices that fit in our hands. In those circuits, etched thinner than a human hair, the electric echoes of cosmic distances are recorded. That reversal, the vast dependent on the small, is another reminder that scale is relational. Wonder doesn't belong only to the giants, it belongs equally to the precise. If you stand outside at night and look up, your body becomes the measure of the universe. The arc of your outstretched arm defines the horizon. The tilt of your head aligns you with the stars. The rotation of the planet carries you eastward beneath the constellations at a speed faster than any jet. Every heartbeat marks the passage of another 10,000 kilometers in orbit around the sun. Without trying, you're moving through space on scales you can barely comprehend. The human measure isn't about shrinking the universe, it's about finding scale within participation. You're not apart from the movement, you are part of it. That realization is one of the quiet truths of astronomy. We began by looking outward, thinking we were small observers watching something large, but in the act of observing we discovered connection. Our existence is bound to the same forces that shape planets and stars. The human measure doesn't reduce the cosmos to comfort, it brings the cosmos into empathy. Every measurement is a form of conversation between awareness and immensity, between the mind that wonders and the system it inhabits. In the end, the numbers we use to describe the solar system are only scaffolding. Behind them lies something that cannot be calculated, the feeling of being within it. The human measure transforms scale into meaning, turning distances into relationships, turning size into perspective. The sun is vast, the planets are many, the galaxy is endless, but the understanding of them depends on the scale that asks the questions. Drifting outward in thought, we can see the full pattern at once. The small world within the large system, the system within the galaxy within the universe, all of it held within perception. The human measure completes the loop. It returns vastness to intimacy. What began as a question about how tiny Earth is becomes a reflection of how capable the mind is. Even in the face of immensity, the act of wondering turns distance into connection. If you trace everything we've explored, the warmth of the sun, the rings of Saturn, the light that takes hours to cross the solar system, it all narrows down again to one small world turning quietly in the dark. After all the distances and comparisons, after all the measures and magnitudes, we return to Earth, the dust grain called home. From far away it seems almost nothing. Up close, It contains everything. Between those two truths lies the meaning of the smallest greatness. Greatness, as we tend to imagine it, belongs to size. We associate it with scale, with immensity, with dominance. But the farther we've looked into space, the clearer it becomes that greatness is not measured in kilometers or mass. It's measured in pattern, in coherence, in what something can sustain. The giants of the solar system are impressive, but they are not alive. The sun is powerful, but it cannot think. Earth, small and finite, carries within it the one quality that transforms existence into significance: awareness. From here, standing on this small world, everything large gains its meaning through perception. The storms on Jupiter, the light of the sun, the silence of the Kuiper belt, all become known only because there is something here to notice them. Without observation, the universe would still unfold, but it would unfold unseen. The awareness that flickers within this tiny biosphere turns process into experience, existence into story. That transformation is the quiet greatness of smallness. If you could see Earth from the distance of the outer planets, it would appear as a point of pale light. No continents, no clouds, no movement, just a speck. Yet within that speck there are oceans shifting with tides, forests breathing carbon in and oxygen out, cities lit by the reflections of their own curiosity. There are people standing beneath stars, asking questions about the light that reaches them. That activity, invisible from space, changes the meaning of the entire system. The solar system without life would be architecture. With life, it becomes narrative. Every discovery we've made about the cosmos begins here. The telescopes, the mathematics, the spacecraft. They all start from one small surface under one small sky. From here, we've mapped the orbits of worlds that no one had ever seen, sent machines to the edge of the sun's influence, captured light that began its journey before our species existed. Each of those acts is small in effort but vast in reach. The greatness of humanity is not that we are powerful, it's that we are curious. The solar system itself seems indifferent to that curiosity. The sun burns whether we look at it or not. Jupiter's storms will rage for centuries whether we measure them or ignore them. The planets turn in their orbits, silent, complete. Yet the act of noticing changes everything for us. It turns repetition into rhythm, motion into music. It gives us a sense of place in a pattern that does not require us but includes us nonetheless. The universe becomes participatory the moment it is perceived. When astronauts describe seeing Earth from orbit, the image always carries the same paradox. From that distance, the world looks small enough to cover with a thumb, and yet it contains all meaning. The thin blue arc of atmosphere, the bright curve of oceans, the faint glimmer of land, fragile, finite, glowing. They describe feeling both humbled and connected, both insignificant and essential. It's not contradiction, it's perspective. They see the smallest greatness with their own eyes. That feeling doesn't require a rocket to reach. It arrives quietly in the mind when you look at the night sky and recognize that the light falling through your atmosphere has travelled for millions of years to get there. You stand at the receiving end of time and distance, held upright by gravity, warmed by radiation from a star so far away, its surface light left minutes before you were aware of it. In that moment, your smallness and your belonging are the same thing. The phrase, "the smallest greatness," captures that unity. It describes a world that is both trivial and irreplaceable, both one among billions and the only one like itself we know. It describes a scale of meaning that grows inward instead of outward. The more we discover about the immensity of space, the more the significance of this small world sharpens. The vastness doesn't dilute importance, it defines it. Because in all that distance, in all that darkness, this is where light meets awareness. Every measurement we've taken, the kilometers between planets, the speed of light, the weight of the sun, frames a stage so enormous that it seems almost indifferent to us. Yet the stage alone is not the story. The story is the moment of recognition within it, The world doesn't need to be large to be great. It needs to be complete. And Earth, for all its fragility and limits, is complete in ways the Titans are not. It holds life, time, language, and the ability to wonder about all of them. From another star system, if anyone could see us, our planet would not stand out. It would be one faint glimmer among billions, circling a quiet yellow star in an ordinary arm of an ordinary galaxy. But if they looked closer, if they could somehow hear the electromagnetic noise we've been sending into space for a century, they would find something rare. They would find signals that carry intention, music, mathematics, patterns of thought. They would find a world where awareness speaks. The greatness of this smallness lies in that sound, the sound of consciousness crossing silence. The same photons that left the sun hours ago now reflect off the oceans, scatter in the clouds, and return outward, carrying information about our existence. Somewhere, someday, they may reach another observer. To them, Earth will appear as a flickering dot, a moving mirror of light. In those flickers lies the record of our seasons, our storms, our civilizations. Even if no one ever sees it, the light still goes, still travels, carrying the signature of a living world into the dark. The solar system will not last forever. The sun will change, expand, fade. The planets will drift, their orbits disturbed by time and passing stars. The dust and light will disperse into the galaxy. But the pattern we are part of, the continuity of matter and energy, will persist. The atoms that make up our bodies and our planet will go on, recycled into new stars and worlds. The smallest greatness is not eternal form. It is eternal motion, the continuation of connection. And here, in this moment, within that motion, you exist. You, a being of dust and thought, sitting on a planet so small it vanishes from view before you finish this sentence. You're part of a system older than imagination and wider than comprehension. The warmth you feel, the air you breathe, the light you see, all come from the same processes that govern the stars. You're not beside the universe, you're inside it. The smallest greatness is the realization that you do not have to be large to matter. You only have to belong. The marble beneath your feet, spinning softly in the sun's glow, is not a point of insignificance. It's a point of convergence, where the forces of the cosmos become conscious of themselves. When you look outward at the night sky, you are the universe looking back. So rest easy in that thought. The distances are endless, the numbers vast, but the meaning is immediate. The stars will keep burning, the planets will keep turning, and the dust grain called home will keep drifting, carrying its light through the dark. In that light, in that smallness, is everything.